Chapter 1 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 1 Introduction. Though by familiarity made commonplace, the weather is one of the most important topics of conversation, and has constant bearings upon the work and prospects of businessmen and men of pleasure. The state of the weather is the password when people meet on the country road. We could not do without the humble talisman. A fine day comes spontaneously to the lips, whatever be the state of the atmosphere, unless it is peculiarly and strikingly repulsive. Then a bitter day would take the place of the expression. Yet I have heard terrible good weather as often as terrible bad day among country people. Scarcely a friendly letter is penned without a reference to the weather, as to what has been, is, or may be. It is a new stimulus to a lagging conversation at any dinner table. All are so dependent on the weather, especially those getting up in years or of delicate health. I remember when at Strathpeffer, the great health resort in the north of Scotland, in 1885, an anxious invalid at the pump asking a weather-beaten, rheumatic old gamekeeper what sort of a day it was to be, considering that it had been wet for some time. The keeper crippled to the barometer outside the doorway, and returned with the matter-of-fact answer, "She's far doon to-day nor she was up yestreen." The barometer had evidently fallen during the night, and what are we to expect? Sadly inquired the invalid. "It'll be either very wet or moy rain." A poor consolation. Most men who are bent on business or pleasure, and all dwellers in the country who have the instruments, make a first call at the barometer in the lobby, or the aneroid in the breakfast parlor, to see what she says. A good rise of the black needle, that is to the right, above the yellow needle is a source of rejoicing, as it will likely be clear, dry, and hard weather. A slight fall, that is to the left, causes anxiety as to coming rain, and a big depression forebodes much rain or a violent storm of wind. In either case of fall, the shudders come over the eyes of the observer. Next, even before breakfast, a move is made to the self-registering thermometer, set the night before, on a stone a couple of feet above the grass. A good reading, above the freezing point in winter and much above it in summer, indicates the absence of killing rime that are generally followed by rain. A very low register accounts for the feeling of cold during the night, though the fires were not out, and predicts precarious weather. Ordinarily careful observers, as I, who have been in one place for more than 30 years, can, with the morning indications of these two instruments, come pretty sure of their prognostics of the day's weather. Of course, the morning newspaper is carefully scanned as to the weather forecasts from the London Meteorological Office. Direction of wind, warm, mild, or cold, rain or fair, and so on. And in general these indications are wonderfully accurate for 24 hours, though the 3 days prognostics seem to stretch a point. We are hardly up to that yet. The lower animals are very sensitive as to the state of approaching extremes of weather. The CBS, referring to seagulls over the inland leas during plowing, are ordinary indicators of stormy weather. Wind is sure to follow violent wheelings of crows. Beware of rain when the sheep are restive, rubbing themselves on tree stumps. But all are familiar with Jenner's prognostics of rain. Science has come to the aid of ordinary weather lore during the last 20 years by leaps and bounds. Time-honored notions and revered fictions around which the hallowed associations of our early training fondly and firmly cling must now yield to the exact handling of modern science, and with reluctance we have to part with them. Yet there is in all a fascination to account for certain ordinary phenomena. The man in the street, as well as the strong reading man, wishes to know the why and the how of weather forecasting. They are anxious to have weather phenomena explained in a plain, interesting, but accurate way. The freshness of the marvelous results has an irresistible charm for the open mind, keen for useful information. The discoveries often seem so simple that one wonders why they were not made before. Until about 20 years ago, meteorology was comparatively far back as a science, and in one important branch of it, no one has done more to put weather lore on a scientific basis than Dr. John Aitken, Fellow of the Royal Society, who has very kindly given me his full permission to popularize what I like of his numerous and very valuable scientific papers in the Transactions of the Royal Society of Edinburgh. This I have done my best to carry out in the following pages. The way of putting it is my only claim. Many scientific men are decoyed on in the search for truth with a spell unknown to others. The anticipation of the results sometimes amounts to a passion. Many wrong tracks do they take, yet they start afresh, just as the detective has to take several courses before he hits upon the correct scent. When they succeed, they experience a pleasure which is indescribable. To them, fame is more than a mere fancied life in others' breath. Dr. Aitken's continued experiments, often of rare ingenuity and brilliancy, show that no truth is altogether barren, and even that which looks at first sight the very simplest and most trivial may turn out fruitful in precious results. Small things must not be overlooked, for great discoveries are sometimes at a man's very door. Dr. Aitken has shown us this in many of his discoveries, which have revolutionized a branch of meteorology. Prudence, patience, observing power, and perseverance in scientific research will do much to bring about unexpected results, and not more so in any science than in accounting for weather lore on a rational basis, which it is in the power of all my readers to further. The old order changes, giving place to new. With kaleidoscopic variety, nature's face changes to the touch of the anxious and reverent observer, and some of these curious weather views will be disclosed in these pages, so as, in a brief but readable way, to explain the weather, and lay a safe basis for probable forecastings, which will be of great benefit to the man of business as well as the man of pleasure. Felix qui potuit rerum cognoscere causas. Virgil. End of Chapter 1. Introduction. Recording by Pamela Krantz.
Chapter 2 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A recording by Marianne. Meteorology by J. G. McPherson. Chapter 2. The Formation of Dew. The writer of the book of Job gravely asked the important question, Who hath begotten the drops of dew? We repeat the question in another form. Whence comes the real dew? Does it fall from the heavens above, or does it rise from the earth beneath? Until about the beginning of the 17th century, scientific men held the opinion of ordinary observers that dew fell from the atmosphere. But there was then a reaction from this theory, for Nardius defined it as an exhalation from the earth. Of course, it was well known that dew was formed by the precipitation of the vapor of the air upon a colder body. You see that any day for yourself by bringing a glass of very cold water into a warm room. The outer surface of the glass is dimmed at once by the moisture from the air. M. Pickett was puzzled when he saw that a thermometer, suspended 5 feet above the ground, marked a lower temperature on clear nights than one suspended at a height of 75 feet, because it was always supposed that the cold of evening descended from above. Again he was puzzled when he observed that a buried thermometer read higher than one on the surface of the ground. Until recently, the greatest authority on dew was Dr. Wells, who carefully converged all the rays of scientific light upon the subject. He came to the conclusion that dew was condensed out of the air. But the discovery of the true theory was left to Dr. John Aitken, F.R.S., a distinguished observer and practical physicist, of whom Scotland has reason to be proud. About 20 years ago he made the discovery, and it is now accepted by all scientific men on the Continent as well as in Great Britain. What first caused him to doubt Dr. Wells's theory, so universally accepted, that dew is formed of vapor existing at the time in the air, and to suppose that dew is mostly formed of vapor rising from the ground, was the result of some observations made in summer on the temperature of the soil at a small depth under the surface, and of the air over it, after sunset and at night. He was struck with the unvarying fact that the ground, a little below the surface, was warmer than the air over it. By placing a thermometer among stems below the surface, he found that it registered 18 degrees Fahrenheit higher than one on the surface. So long, then, as the surface of the ground is above the dew point, i.e., the temperature when dew begins to be formed, the vapor must rise from the ground. This moist air will mingle with the air which it enters, and its moisture will be condensed and form dew whenever it comes in contact with a surface cooled below the dew point. You can verify this by simple experiments. Take a thin, shallow metal tray, painted black, and place it over the ground after sunset. On dewy nights the inside of the tray is dewed, and the grass inside is wetter than that outside. On some nights there is no dew outside the tray, and on all nights the deposit on the inner is heavier than on the outer side. If wool is used in the experiments, we are reminded of one of the forms of the dewing of Gideon's fleece. The fleece was bedewed when all outside was dry. You therefore naturally and rightly come to the conclusion that far more vapor rises out of the ground during the night than condenses as dew on the grass, and that this vapor from the ground is trapped by the tray. Much of the rising vapor is generally carried away by the passing wind, however gentle. Hence we have it condensed as dew on the roofs of houses and other places where you would think that it had fallen from above. The vapor rising under the tray is not diluted by the mixture with the drier air which is occasioned by the passing wind. Therefore, though only cooled to the same extent as the air outside, it yields a heavier deposit of dew. If you place the tray on bare ground, you will find on a dewy night that the inside of the tray is quite wet. On a dewy night you will observe that the under part of the gravel of the road is dripping wet when the top is dry. You will find, too, that around pieces of iron and old implements in the field there is a very marked increase of grass, owing to the deposit of moisture on these articles, moisture which has been condensed by the cold metal from the vapor-charged air, which has risen from the ground on dewy nights. But all doubt on this important matter is removed by a most successful experiment with a fine balance, which weighs to 1/4 of a grain. If vapor rises from the ground for any length of time during dewy nights, the soil which gives off the vapor must lose weight. To test this, cut from the lawn a piece of turf 6 inches square and 1/4 of an inch thick. Place this in a shallow pan, and carefully note the weight of both turf and pan with a sensitive balance. To prevent loss by evaporation, the weighing should be done in an open shed. Then place the pan and turf at sunset in the open cut. 5 hours afterward remove and weigh them, and it will be found that the turf has lost a part of its weight. The vapor which rose from the ground during the formation of the dew accounts for the difference of weight. This weighing test will also succeed on bare ground. When dealing with hoar-frost, which is just frozen dew, we shall find evidence of the rising of the dew from the ground. You know the beautiful song, Annie Laurie, which begins with Maxwelton's braes are bonny, where early fa's the dew. Well, you can no longer say that the dew falls, for it rises from the ground. The song, however, will be sung as sweetly as ever, for the spirit of true poetry defies the cold letter of science. End of chapter 2. Chapter 3 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Mary Ann. Meteorology by J. G. McPherson. Chapter 3. True and false dew. Ever since men could observe and think, they have admired the diamond globules sparkling in the rising sun. These dewdrops were considered to be shed from the bosom of the morn into the blooming flowers and rich grass leaves. Ballantyne's beautiful song of providential care tells us that ilka blade of grass keeps its ain drap of dew. But, alas, we have to bid good-bye to the appellation dewdrop. What was popularly and poetically called dew is not dew at all. Then what is it? On what we have been accustomed to call a dewy night, after the brilliant summer sun has set and the stars begin to peep out of the almost cloudless sky, let us take a look at the produce of our vegetable garden. On the broccoli are found glistening drops, but on the peas growing next to them we find nothing. A closer examination shows us that the moisture on the plants is not arranged as would be expected from the ordinary laws of radiation and condensation. There is no generally filmy appearance over the leaves. The moisture is collected in little drops placed at short distances apart along the edges of the leaves all round. Now, place a lighted lantern below one of the blades of the broccoli, and a revelation will be made. The brilliant diamond drops that fringe the edge of the blade are all placed at the points where the nearly colorless veins of the blade come to the outer edge. The drops are not dew at all, but the exudation of the healthy plant, which has been conveyed up these veins by strong root pressure. The fact is that the root acts as a kind of force pump and keeps up a constant pressure inside the tissues of the plant. One of the simplest experiments suggested by Dr. Aitken is to lift a single grass plant with a clod of moist earth attached to it and place it on a plate with an inverted tumbler over it. In about an hour drops will begin to exude, and the tip of nearly every blade will be found to be studded with a diamond-like drop. Next, substitute water pressure. Remove a blade of broccoli and connect it by means of an India rubber tube with a head of water of about 40 inches. Place a glass receiver over it so as to check evaporation, and leave it for an hour. The plant will be found to have excreted water freely, some parts of the leaves being quite wet, while drops are collected at the places where they appeared at night. If the water pressed into the leaf is colored with aniline blue, the drops when they first appear are colorless, but before they grow to any size the blue appears, showing that little water was held in the veins. The whole leaf soon gets colored of a fine deep blue-green, like that seen when vegetation is rank. This shows that the injected liquid has penetrated through the whole leaf. Again, the surfaces of the leaves of these drop-exuding plants never seem to be wetted by the water. It is because of the rejection of water by the leaf's surface that the exuded moisture from the veins remains as a drop. These observations and experiments establish the fact that the drops which first make their appearance on grass on dewy nights are not dewdrops at all, but exuded watery juices of the plants. If we now look at dead leaves, we shall find a difference of formation of the moisture on a dewy night. The moisture is spread equally over, where equally exposed. The moisture exuded by the healthy grass is always found at a point, situated near the tip of the blade, forming a drop of some size. But the true dew collects later on, evenly over all the blade. The false dew forms a large glistening diamond drop, whereas the true dew coats the blade with a fine pearly luster. Brilliant globules are produced by the vital action of the plant, especially beautiful when the deep red setting sun makes them glisten, all the tremble, with gold light, while an infinite number of minute but shining opal-like particles of moisture bedecks the blade surfaces, in the form of the gentle dew, like that which kept the heart of Eden green, before the useful trouble of the rain. End of chapter 3. Chapter 4 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. Meteorology by J.G. McPherson. Chapter 4. Hoar-Frost. All in this country are familiar with the beauty of hoar-frost. The children are delighted with the funny figures on the glass of the bedroom window on a cold winter morning. Frost is a wonderful artist. During the night he has been dipping his brush into something like diluted schist, and laying it gracefully on the smooth panes. And, as you walk over the meadows, you observe the thin white films of ice on the green pasture, and the clear, slender blades seem like crystal spears, or the lashes of light that trim the stars. You all know what hoar-frost is, though most in the country give it the expressive name of rime. But you are not all aware of how it is formed. Hoar-frost is just frozen dew. In a learned paper, written in 1784, Professor Wilson of Glasgow made this significant remark. This is a subject which, besides its entire novelty, seems, upon other accounts, to have a claim to some attention. He observed, in that exceptionally cold winter, that, when sheets of paper and plates of metal were laid out, all began to attract hoar-frost as soon as they had time to cool down to the temperature of the air. He was struck with the fact that, when the thermometer indicated 36 degrees of frost a few feet above the ground, and 44 degrees of frost at the surface of the snow, there were only 8 degrees of frost at a point 3 inches below the surface of the snow. If he had only thought of placing the thermometer on the grass under the snow, he would have found it to register the freezing point only, and had he inserted the instrument below the ground, he would have found it registering a still higher temperature. That fact would have suggested to him the formation of hoar-frost, that the water vapor from the warm soil was trapped by a cold stratum of air and frozen when in the form of dew. One of the most interesting experiments, without apparatus, which you can make is in connection with the formation of hoar-frost when there is no snow on the ground in very cold weather. If it has been a bright, clear, sunny day in January, the effect can be better observed. Look over the garden, grass, and walks on the morning after the intense cold of the night. Big plane tree leaves may be found scattered over the place. You see little or no hoar-frost on the upper surface of the leaves, but turn up the surface next the earth, or the road, or the grass, and what do you see? You have only to handle the leaf in this way to be brightly astonished. A thick white coating of hoar-frost, as thick as a layer of snow, is on the under surface. If a number of leaves have been overlapping each other, there will be no coating of hoar-frost under the top leaves, but when you reach the lowest layer, next the bare ground, you will find hoar-frost on the under surface of the leaves. Now that is positive proof that the hoar-frost has not fallen from the air, but has risen from the earth. The sun's heat on the previous day warmed the earth. This heat the earth retained till evening. As the air chilled, the water vapor from the warmer earth rose from its surface, and was arrested by the cold surface of the leaves. So cold was that surface that it froze the water vapor when rising from the earth, and formed hoar-frost in very large quantities. When this happens later on in the season, one may be almost sure of having rain in the forenoon. As hoar-frost is just frozen dew, I can even more surely convince you of the formation of hoar-frost as rising from the ground, by observations made by me at my manse in Strathmore in June 1892. I mention this particularly because then was the most favorable testing time that has ever occurred during meteorological observations. June 9th was the warmest June day, with one exception, for 20 years. The thermometer reached 83 degrees Fahrenheit in the shade. Next day was the coldest June day, with one exception, for 20 years, when the thermometer was as low as 51 degrees in the shade. But during the night my thermometer on the grass registered 32 degrees, the freezing point. On the evening of the sultry day I examined the soil at 10 o'clock. It was damp, and the grass round it was filmy moist. The leaves of the trees were crackling dry, and all above was void of moisture. The air became gradually chilly, and as gradually the moisture rose in height on the shrubs and lower branches of small trees. The moon shone bright, and the stars showed their clear, chilly eyes. The soil soon became quite wet. The low grass was dripping with moisture, and the longer grass was becoming dewed. This gave the best natural evidence of the rising of the dew that I ever witnessed. That everything was favorable for the observation. The cold air incumbent on the rising, warm, moist vapor from the soil, fixing the dew point, when the projecting blades seized the moisture greedily and formed dew. Had the temperature been a little below the freezing point, hoar-frost would have been beautifully formed. End of chapter 4.
Chapter 5 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jason Mills. Meteorology by J.G. McPherson. Chapter 5. Fog. To many, nothing is more troublesome than a dense fog in a large town. It paralyzes traffic. It is dangerous to pedestrians. It encourages theft. It chokes the asthmatic and chills the weak-lunged. In the country it is disagreeable enough, but never so intensely raw and dense as in the city. On the sea, too, the fog is disagreeable and fraught with danger. The foghorn is heard in its deep, sombre note from the lighthouse tower when the strong artificial light is almost useless. But a peculiar sense of stagnation possesses the dweller of the large town when enveloped in a dense fog. Sometimes during the day, through a thinner portion, the sun will be dimly seen in copper hue, like the moon under an eclipse. The smoke-impregnated mass assumes a peculiar pea-soup colour. Now, what is this fog? How is it formed? It has been ascertained that fogs are dependent upon dust for their formation. Without dust there could be no fogs. There would be only dew on the grass and road. Instead of the dust-impregnated air that irritates the housekeeper, there would be the constant dripping of moisture on the walls, which would annoy her more. Ocular demonstration can testify to this. If two closed glass receivers be placed beside each other, the one containing ordinary air and the other filtered air, i.e. air deprived of its dust by being driven through cotton wool, and if jets of steam be successively introduced into these, a strange effect is noticed. In the vessel containing common air, the steam will be seen rising in a dense cloud. Then a beautiful white foggy cloud will be formed, so dense that it cannot be seen through. But in the vessel containing the filtered air, the steam is not seen at all. There is not the slightest appearance of cloudiness. In the one case, where there was the ordinary atmospheric dust, fog at once appeared. In the other case, where there was no dust in suspension, the air remained clear and destitute of fog. Invisible dust, then, is necessary in the air for the formation of fogs. The reason of this is that a free surface must exist for the condensation of the vapour particles. The fine particles of dust in the air act as free surfaces, on which the fog is formed. Where there is abundance of dust in the air, and little water vapour present, there is an over-proportion of dust particles, and the fog particles are, in consequence, closely packed, but light in form and small in size, and take the lighter appearance of fog. Accordingly, if the dust is increased in the air, there is a proportionate increase of fog. Every fog particle, then, has embosomed in it an invisible dust particle. But whence comes the dust? From many sources. It is organic and inorganic. So very fine is the inorganic dust in the atmosphere that, if the 2,000th part of a grain of fine iron be heated, and the dust be driven off and carried into a glass receiver of filtered air, the introduction of a jet of steam into that receiver would at once occasion an appreciable cloudiness. This is why fogs are so prevalent in large towns. Next to the minute brine particles, driven into the air as fog forms above the ocean surface, are the burnt sulphur particles, emanating from the chimneys in towns. The brilliant flame as well as the smoky flame is a fog producer. If gas is burnt in filtered air, intense fog is produced when water vapour is introduced. Products of combustion from a clear fire and from a smoky one produce equal fogging. The fogs that densely fill our large towns are generally less bearable than those that veil the hills and overhang the rivers. It is the sulphur, however, from the consumed coals, which is the active producer of the fogs of a large town. The burnt sulphur condenses in the air to very fine particles, and the quantity of burnt sulphur is enormous. No less than 7.5 million tons of coal are consumed in London. Now, the average amount of sulphur in English coal is 1¼ per cent. That would give no less than 93,750 tons of sulphur burned every year in London fires. Now, if we reckon that on average twice the quantity of coals is consumed there on a winter day that is consumed on a summer day, no less than 347 tons of the products of combustion, in extremely fine particles, are driven into the superincumbent air of London every winter day. This is an enormous quantity, quite sufficient to account for the density of the fogs in that city. End of Chapter 5. Recording by Jason Mills. Chapter 6 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jason Mills. Meteorology by J.G. McPherson. Chapter 6. The Numbering of the Dust. If the shutters be all but closed in a room, when the sun is shining in, myriads of floating particles can be seen glistening in the stream of light. Their number seems inexhaustible. According to Milton, the follies of life are thick and numberless as the gay motes that people the sunbeams. Can these, then, be counted? Yes. Dr. Aitken has numbered the dust of the air. I shall never forget my rapt astonishment the day I first numbered the dust in the lecture room of the Royal Society of Edinburgh, with his instrument and under his direction. This wonderfully ingenious instrument was devised on this principle, that every fog particle has entombed in it an invisible dust particle. A definite small quantity of common air is diluted with a fixed large quantity of dustless air, i.e. air that has been filtered through cotton wool. The mixture is allowed to be saturated with water vapour. Then the few particles of dust seize the moisture, become visible in fine drops, fall on a divided plate, and are there counted by means of a magnifying glass. That is the secret. I shall now give you a general idea of the apparatus. Into a common glass flask of carafe shape, and flat-bottomed, of 30 cubic inches capacity, are passed two small tubes, at the end of one of which is attached a small square silver table, 1 inch in length. A little water having been inserted, the flask is inverted, and the table is placed exactly 1 inch from the inverted bottom, so that the contents of air right above the table are 1 cubic inch. This observing table is divided into 100 equal squares, and is highly polished, with the burnishing all in one direction, so that during the observations it appears dark, when the fine mist particles glisten opal-like with the reflected light, in order that they may be more easily counted. The tube to which the silver table is attached is connected with 2 stopcocks, one of which can admit a small measured portion of the air to be examined. The other tube in the flask is connected with an air pump of 10 cubic inches capacity. Over the flask is placed a covering, coloured black in the inside. In the top of this cover is inserted a powerful magnifying glass, through which the particles on the silver table can be easily counted. A little to the side of this magnifier is an opening in the cover, through which light is concentrated on the table. To perform the experiment, the air in the flask is exhausted by the air pump. The flask is then filled with filtered air. 1/10 of a cubic inch of the air to be examined is then introduced into the flask, and mixed with the 30 cubic inches of dustless air. After 1 stroke of the air pump, this mixed air is made to occupy an additional space of 10 cubic inches, and this rarefying of the air so chills it that condensation of the water vapour takes place on the dust particles. The observer, looking through the magnifying glass upon the silver table, sees the mist particles fall like an opal shower on the table. He counts the number on a single square in 2 or 3 places, striking an average in his mind. Suppose the average number upon a single square were 5, then on the whole table there would be 500, and these 500 particles of dust are those which floated invisibly in the cubic inch of mixed air right above the table. But as there are 40 cubic inches of mixed air in the flask and barrel, the number of dust particles in the whole is 20,000. That is, there are 20,000 dust particles in the same quantity of common air, 1/10 of a cubic inch, which was introduced for examination. In other words, a cubic inch of the air contained 200,000 dust particles, nearly 250,000. The day I used the instrument, we counted 4 million of dust particles in a cubic inch of the air outside of the room, due to the quantity of smoke from the passing trains. Dr. Aitken has counted in 1 cubic inch of air immediately above a Bunsen flame the fabulous number of 489 million of dust particles. A small instrument has been constructed which can bring about results sufficiently accurate for ordinary purposes. It is so constructed that when the different parts are unscrewed, they fit into a case 4½ inches by 2½ by 1¼ deep, about the size of an ordinary cigar case, After knowing this, we are apt to wonder why our lungs do not get clogged up with the enormous number of dust particles. In ordinary breathing, 30 cubic inches of air pass in and out at every breath, and adults breathe about 15 times every minute. But the worn lung surface repels the colder dust particles, and the continuous evaporation of moisture from the surface of the air tubes prevents the dust from alighting or clinging to the surface at all. End of Chapter 6. Recording by Jason Mills.
Chapter 7 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Gonzalez. Meteorology by J.G. McPherson. Chapter 7. Dust in Atmospheric Phenomena. Dr. Aiken has devoted a vast amount of attention to the enumeration of dust particles in the air, on the continent as well as in Scotland, to determine the effects of the variation in number. On his first visit to the air in 1890, he counted with the instrument 12,000 dust particles in a cubic inch of the air, whereas in the following year he counted 250,000. He observed, however, that where there was least dust, the air was very clear, whereas with the maximum dust there was a very thick haze. At Mentone, the corresponding number was 13,000, when the wind was blowing from the mountains, but increased to 430,000, when the wind was blowing from a populous town. On his first visit to Rigi-Kulm, Switzerland, the air was remarkably clear and brilliant, and the corresponding number never exceeded 33,000, but on his second visit, he counted no less than 166,000. This was accounted for by a thick haze, which rendered the lower Alps scarcely visible. The upper limit of the haze was well defined, and though the sky was cloudless, the sun looked like a harvest moon, and required no eagle's eye to keep fixed on it. Next day there was a violent thunderstorm. At 6 p.m. the storm commenced, and 60,000 dust particles to the cubic inch of the air were registered, but in the middle of the storm he counted only 13,000. There was a heavy fall of hail at this time, and he accounts for the diminution of dust particles by the downrush of purer upper air, which displaced the contaminated lower air. At the Lake Luzerne, there was an exceptional diminution of the number in the course of an hour, viz., from 171,000 to 28,000 in a cubic inch. On looking about, he found that the direction of the wind had changed, bringing down the purer upper air to the place of observation. The bending downwards of the trees by the strong wind showed that it was coming from the upper air. Returning to Scotland, he continued his observation at Ben Nevis, at King Airloch, opposite Appin. Mr. Rankin using the instrument at the top of the mountain. These observations showed in general that on the mountain, southerly, southeasterly, and easterly winds were more impregnated with dust particles, sometimes containing 133,000 per cubic inch. Northerly winds brought pure air. The observations at sea level showed a certain parallelism to those in the summit of the mountain. With a northwesterly wind, the dust particles reached a low number of 300 per cubic inch, the lowest recorded at any low-level station. The general deduction which he made from his numerous observations during these 2 years are that 1. Air coming from inhabited districts is always impure. 2. Dust is carried by the wind to enormous distances. 3. Dust rises to the tops of the mountain during the day. 4. With much dust there is much haze. 5. High humidity causes great thickness of the atmosphere, if accompanied by a great amount of dust, whereas there is no evidence that humidity alone has any effect in producing thickness. 6. And there is generally a high amount of dust with high temperature, and a low amount of dust with low temperature. End of Chapter 7. Recording by April Gonzalez, Cavite, Philippines.
Chapter 8 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patty Cunningham. Meteorology by J.G. McPherson. Chapter 8, A Fog Counter. Next to the enumeration of the dust particles in the atmosphere is the marvelous accuracy of counting the number of particles in a fog. The same ingenious inventor has constructed a fog counter for the purpose, and the number of fog particles in a cubic inch can be ascertained. This instrument consists of a glass micrometer divided into squares of a known size, and a strong microscope for observing the drops on the stage. The space between the micrometer and the microscope is open, so that the air passes freely over the stage, and the drops that fall on its surface are easily seen. These drops are very small. Many of them, when spread on the glass, are no more than the 500th of an inch in diameter. In observing these drops, the attention requires to be confined to a limited area of the stage, as many of the drops rapidly evaporate, some almost as soon as they touch the glass, whilst the large ones remain a few seconds. In one set of Dr. Atkins' observations in February 1891, the fog was so thick that objects beyond 100 yards were quite invisible. The number of drops falling per second varied greatly from time to time. The greatest number was 323 drops per square inch in 1 second. The high number never lasted for long, and in the intervals the number fell as low as 32, or to 1/10. If we knew the size of these drops, we might be able to calculate the velocity of their fall, and from that obtain the number in a cubic inch. An ingenious addition is put to the instrument in order to ascertain this directly. It is constructed so as to ascertain the number of particles that fall from a known height. Under a low-power microscope, and concentric with it, is mounted a tube 2 inches long and 1½ inch in diameter, with a bottom and a cover, which are fixed to an axis parallel with the axis of the tube, so that, by turning a handle, these can be slid sideways, closing or opening the tube at both ends when required. In the top is a small opening corresponding to the lens of the microscope, and in the center of the bottom is placed the observing stage illumined by a spot mirror. The handle is turned and the ends are open to admit the foggy air. The handle is quickly reversed and the ends are closed, enabling the observer to count on the stage all the fog particles in the 2 inches of air over it. The number of dust particles in the air which become centers of condensation depends on the rate at which the condensation is taking place. The most recent observations show that quick condensation causes a large number of particles to become active, whereas slow condensation causes a small number. After the condensation has ceased, a process of differentiation takes place, the larger particles robbing the smaller ones of their moisture owing to the vapor pressure at the surface of the drops of large curvature being less than at the surface of drops of smaller curvature. By this process, the particles in a cloud are reduced in number. The remaining ones, becoming larger, fall quicker. The cloud thus becomes thinner for a time. A strong wind suddenly arising will cause the cloud particles to be rapidly formed. These will be very numerous but very small, so small that they are just visible with great care under a strong magnifying lens used in the instrument. But in slowly formed clouds, the particles are larger and therefore more easily visible to the naked eye. Though the particles in a fog are slightly finer, the number is about the same as in a cloud, that is, generally. As clouds vary in density, the number of particles varies. Sometimes in a cloud one cannot see farther than 30 yards, whereas in a few minutes it clears up a little so that we can see 100 yards. Of course, the denser the cloud, the greater the number of water particles falling on the calculating stage of the instrument. Very heavy falls of cloud particles seldom last more than a few seconds, the average being about 325 on the square inch per second, the maximum reaching to 1290. This is about 4 times the number counted in a fog. Yet the particles are so very small that they evaporate instantly when they reach a slight increase of temperature. End of Chapter 8. Recording by Patty Cunningham.
Chapter 9 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J.G. McPherson. Chapter 9. Formation of Clouds. In our ordinary atmosphere, there can be no clouds without dust. A dust particle is the nucleus that at a certain humidity becomes the center of condensation of the water vapor so as to form a cloud particle, and a collection of these forms a cloud. This condensation of vapor round a number of dust particles in visible form gives rise to a vast variety of cloud shapes. There are 2 distinct ways in which the formation of clouds generally takes place. Either a layer of air is cooled in a body below the dew point, or a mass of warm and moist air rises into a mass which is cold and dry. The first forms a cloud, called, from being a layer, stratus. The second forms a cloud, called, from its heap appearance, cumulus. The first is widely extended and horizontal, averaging 1,800 feet in height. The second is convex or conical, like the head of a sheaf, increasing upward from a level base, averaging from 4,500 feet to 6,000 feet in height. There are endless combinations of these 2, but at the height of 27,000 feet, where the cloud particles are frozen, the structure of the cloud is finer, like mare's tails, receiving the name cirrus. When the cirrus and cumulus are combined in well-defined roundish masses, what is familiarly described as a mackerel sky is beautifully presented. The dark mass of cloud called nimbus is the threatening rain cloud, about 4,500 feet in height. At the International Meteorological Conference at Munich in 1892, 12 varieties of clouds were classified, but those named above are the principal. In a beautiful sunset, one can sometimes notice 2 or 3 distances of clouds, the sun shedding its golden light on the full front of one set, and only fringing with vivid light the nearer range. Although no man has wrought so hard as Dr. Aitken to establish the principle that clouds are mainly due to the existence of dust particles, which attract moisture on certain conditions, yet even 20 years ago he said that it was probable that sunshine might cause the formation of nuclei and allowed cloudy condensation to take place where there was no dust. Under certain conditions, the sun gives rise to a great increase in the number of nuclei. Accordingly, he has carefully tested a few of the ordinary constituents and impurities in our atmosphere to see if sunshine acted on them in such a way as to make them probable formers of cloud particles. He tested various gases with more or less success. He found that ordinary air, after being deprived of its dust particles and exposed to sunshine, does not show any cloudy condensation on expansion, but when certain gases are in the dustless air, a very different result is obtained. He first used ammonia, putting 1 drop into 6 cubic inches of water in a flask, and sunning this for 1 minute. The result was a considerable quantity of condensation, even with such a weak solution. When the flask was exposed for 5 minutes, the condensation by the action of the sunshine was made more dense. Hydrogen peroxide was tested in the same way, and it was found to be a powerful generator of nuclei. Curious is it that sulphurous acid is puzzling to the experimentalist for cloud formation. It gives rise to condensation in the dark, but sunshine very conclusively increases the condensation. Chlorine caused condensation to take place without supersaturation. Sulphuretted hydrogen, which one always associates with the smell of rotten eggs, gives dense condensation after being exposed to sunshine. Though most of these nuclei, due to the action of sunshine and the gases, remain active for cloudy condensation for a comparatively short space of time, 15 minutes to half an hour, yet the experiments show that it is possible for the cloudy condensation to take place in certain circumstances in the absence of dust. This seems paradoxical in the light of the former beautiful experiments, but in ordinary circumstances, dust is needed for the formation of clouds. However, supposing there is any part of the upper air free from dust, it is now found possible, when any of these gases experimented on be present, for the sun to convert them into nuclei of condensation, and permit of clouds being formed in dustless air, miles above the surface of the earth. In the lower atmosphere there are always plenty of dust particles to form cloudy condensation, whether the sun shines or not. These are produced by the waste from the millions of meteors that daily fall into the air. But in the higher atmosphere, clouds can be formed by the action of the sun's rays on certain gases. This is a great boon to us on the earth, for it assures us of clouds being ever existing to defend us from the sun's extra powerful rays, even when our atmosphere is fairly clear. This is surely of some meteorological importance. End of Chapter 9. Chapter 10 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J.G. McPherson. Chapter 10. Decay of Clouds. From the earliest ages, clouds have attracted the attention of observers. Varied are their forms and colors, yet in our atmosphere there is one law in their formation. Cloud particles are formed by the condensation of water vapor on the dust particles invisibly floating in the atmosphere, up to thousands, and even millions, in the cubic inch of air. But observers have not directed their attention so much to the decay of clouds. In fact, the subject is quite new, and yet how suggestive is the subject? The process of decay in clouds takes place in various ways. A careful observer may witness the gradual wasting away and dilution into thin air of even great stretches of cloud when circumstances are favorable. In May 1896, my attention was particularly drawn to this at my manse in Strathmore. In the middle of that exceptionally sultry month, I was arrested by a remarkable transformation scene. It was the hottest May for 72 years, and the driest for 25 years. The whole parched earth was thirsting for rain. All the morning my eyes were turned to the clouds in the hope that the much-desired shower should fall. Till 10 o'clock the sun was not seen, and there was no blue in the sky, nor was there any haze or fog. But suddenly the sun shone through a thinner portion of the enveloping clouds, and to the north the sky began to open. As if by some magic spell, there was, in a quarter of an hour, more blue to be seen than clouds. At the same time, near the horizon, a haze was forming, gradually becoming denser as time wore on. In an hour the whole clouds were gone, and the glorious orb of day dispelled the moisture to its thin air form. This was a pointed and rapid illustration of the decay from cloud form to haze, and then to pure vapory sky. It was an instance of the reverse process. As the sun cleared through, the temperature in the cloud land rose, and evaporation took place on the surface of the cloud particles, until, by an untraceable but still a gradual process through fog, the haze was formed. Even then the heat was too great for a definite haze, and the water vapor returned to the air, leaving the dust particles in invisible suspension. But clouds decay in another way. This I will illustrate in the next chapter on It Always Rains. What strikes a close observer is the difference of structure in clouds, which are in the process of formation, and those which are in the process of decay. In the former, the water particles are much smaller and far more numerous than in the latter, while the particles in clouds in decay are large enough to be seen with the unaided eye when they fall on a properly lighted measuring table. They are so small in clouds in rapid formation that the particles cannot be seen without the aid of a strong magnifying glass. Observers have assumed that the whole explanation of the fantastic shapes taken by clouds is founded on the process of formation. But Dr. Aitken has pointed out that ripple-marked clouds, for instance, have been clouds of decay. When what is called a cirrostratus cloud mackerel-like against the blue sky, is carefully observed in fine weather, it will be found that it frequently changes the ripple-marked cirrus in the process of decay to vanishing. Where the cloud is thin enough to be broken through by the clear air that is drawn in between the eddies, the ripple markings get nearer and nearer the center as the cloud decays, and at last, when nearly dissolved, these markings are extended quite across the cloud. Whether then we consider the cases of clouds gradually melting away back into their original state of blue water vapor, or the constant fine raining from clouds and reformation by evaporation, or the transformation of such clouds as the cirrostratus into the ripple-marked cirrus, we are forced to the conclusion that in clouds there is not always development, but sometimes degeneration, not always formation, but sometimes decay. End of Chapter 10.
Chapter 11 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J. G. McPherson. Chapter 11. It Always Rains. All are familiar with the answer given by the native of Skye to the irate tourist on that island, who, for the 6th day drenched, asked the question, "Does it always rain here?" "Nah," answered the workman, without at all understanding the joke. "Freilich it snaws." Sometimes it snows. Yet, strange to say, the tourist's question has been answered in the affirmative in every place where a cloud is overhead, visible or invisible. Whenever a cloud is formed, it begins to rain, and the drops shower down in immense numbers, though most minute in size, the playful fancies of the mighty sky. No doubt it is only in certain circumstances that these drops are attracted together so as to form large drops, which fall to the earth in genial showers to refresh the thirsty soil, or in a terrible deluge to cause great destruction. But when the temperature and pressure are not suitable for the formation of what we commonly know as the rain, the fine drops fall into the air under the cloud, where they immediately evaporate from their dust-free surfaces if the air is dry and warm. This is, in other words, the decay of clouds. It is a curious fact that objects in a fog may not be wetted when the number of water particles is great. It seems that these water particles all evaporate so quickly that even one's hand or face is not sensible of being wetted. The particles are minutely small, and they may evaporate even before reaching the warm skin by reason of the heated air over the skin. There is a peculiarly warm sensation in the center of a cumulus cloud, especially when it is not dense. A glow of heat seems to radiate from all points, yet the face and hands are quite dry, and exposed objects are not wetted, but it is really always raining. That is a curious discovery. It is radiant heat that is the cause of the remarkable result. The rays of the sun, which strike the upper part of the cloud, not only heat that surface, but also penetrate the cloud and fall on the surface of bodies within, generating heat there. These heated surfaces again radiate heat into the air attached to them. This warm air receives the fine raindrops in the cloud and dissolves the moisture from the dust particles before the moisture can reach the surfaces exposed. That a vast amount of radiant heat rushes through a cloud is clearly shown by exposing a thermometer with black bulb in vacuo. On some occasions, a thermometer would indicate from 40 degrees to 50 degrees above the temperature of the air, thus proving the surface to be quite dry. These observations have been corroborated on Mount Pilatus, near Lucerne, 1,000 feet higher and more isolated than the Rigi. The summit was quite enveloped in cloud, and though one might naturally conclude that the air was dense with moisture, yet the wooden seats, walls, and all exposed surfaces were quite dry. Strange to say, however, the thermometers hung up got wet rapidly, and the pins driven into the wooden post to support them rapidly became moist. A thermometer lying on a wooden seat stood at 60 degrees, while one hung up read only 48 degrees. This difference was caused by radiant heat. It is well known that when bodies are exposed to radiant heat, they are heated in proportion to their size. The smaller, then, may be moist, when the larger are dry by radiation. The effect of the sun's penetrating heat through the cloud is to heat exposed objects above the temperature of the air, and if the objects are of any size, they are considerably heated and retain their heat more, while at the same time around them is a layer of warm air which is quite sufficient to force the water vapor to leave the dust particles in the fine rain. Hence, seats, walls, posts, etc. are quite dry, though they are in the middle of a cloud. They are large enough to throw off the moisture by the retained heat, or by the large amount of surrounding heat, whereas small bodies, which are not heated to the same degree, and cannot therefore retain their heat so easily, have not heat power sufficient to withstand the moisture, and they become wetted. Hence, by the radiant heat, the large exposed objects are dry in the cloud, whereas small objects are damp, and, in some cases, dripping with wet. The fact is, then, that whenever a cloud overhangs, rain is falling, though it may not reach the earth on account of the dryness of the stratum of air below the cloud, and the heat of the air over the earth. So that on a summer day, with the gold-fringed, fleecy clouds sailing overhead, it is really raining, but the drops, being very small, evaporate long before reaching the earth. As Ariel sings at the end of The Tempest of Shakespeare, "The rain, it raineth every day." It rains, but much of the melting of the clouds is reproduced by a wonderful circularity, the moisture evaporating, seizing other dust particles, forming cloud particles, falling again, and so on ad infinitum during the existing circumstances. End of Chapter 11. It Always Rains. Read by Kara Schallenberg, www.kray.org, in February 2012 in San Diego, California.
Chapter 12 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 12. Haze. What is haze? The dictionary says a fog. Well, haze is not a fog. In a fog, the dust particles in the air have been fully clothed with water vapor. In a haze, the process of condensation has been arrested. Cloudy condensation is changed to haze by the reduction of its humidity. Dr. Aitken invented a simple apparatus for testing the condensing power of dust and observing if water vapor condensed on the deposited dust in unsaturated air. The dust from the air has first to be collected. This is done by placing a glass plate vertically and in close contact with one of the panes of glass in the window by means of a little India rubber solution. The plate being thus rendered colder than the air in the room, the dust is deposited on it. Construct a rectangular box with a square bottom, 1½ inches aside and 3/4 inch deep, and open at the top. Cover the top edge of the box with a thickness of India rubber. Place the dusty plate, a square glass mirror 4 inches aside, on the top of the India rubber and hold it down by spring catches, so as to make the box watertight. The box has been provided with 2 pipes, one for taking in water and the other for taking away the overflow, with the bulb of a thermometer in the center. Clean the dust carefully off 1/2 of the mirror, so that 1/2 of the glass covering the box is clean and the other half dusty. Pour cold water through the pipe into the box, so as to lower the temperature of the mirror, and carefully observe when condensation begins on the clean part and on the dusty part, taking a note of the difference of temperature. The condensation of the water vapor will appear on the dust particles before coming down to the natural dew point temperature of the clean glass. and the difference between the two temperatures indicates the temperature above the dew point at which the dust has condensed the water vapor. Magnesia dust has small affinity for water vapor. Accordingly, it condenses at almost exactly the same temperature as the glass. But gunpowder has great condensing power. All have noticed that the smoke from exploded gunpowder is far more dense in damp than in dry weather. In the experiment, it will be found that the dust from gunpowder smoke begins to show signs of condensing the vapor at a temperature of 9 degrees Fahrenheit above the dew point. In the case of sodium dust, the vapor is condensed from the air at a temperature of 30 degrees above the dew point. Dust collected in a smoking room shows a decidedly greater condensing power than that from the outer air. We can now understand why the glass in picture frames and other places sometimes appears damp when the air is not saturated. When in winter the windows are not often cleaned, a damp deposit may be frequently seen on the glass. Anyone can try the experiment. Clean 1/2 of a dusty pane of glass in cold weather, and the clean part will remain undewed and clear, while the dusty part is damp to the eye and greasy to the touch. These observations indicate that moisture is deposited on the dust particles from air, which is not saturated, and that the condensation takes place while the air is comparatively dry, before the temperature is lowered to the dew point. There is then no definite demarcation between what seems to us clear air and thick haze. The clearest air has some haze, and as the humidity increases, the thickness of the air increases. In all haze, the temperature is above the dew point. The dust particles have only condensed a very small amount of the moisture so as to form haze, before the fuller condensation takes place at the dew point. At the Italian lakes, on many occasions when the air is damp and still, every stage of condensation may be observed in close proximity, not separated by a hard and fast line, but when no one could determine where the clear air ended and the cloud began. Sometimes in the sky overhead a gradual change can be observed from perfect clearness to thick air, and then the cloud. A thick haze may be occasioned by an increased number of dust particles with little moisture, or of a diminished number of dust particles with much moisture, above the point of saturation. The haze is cleared by this temperature rising, so as to allow the moisture to evaporate from the dust particles. Whenever the air is dry and hazy, much dust is found in it. As the dust decreases, the haze also decreases. For example, Dr. Aitken at Kingairloch, in one of the clearest districts of Argyllshire, on a clear July afternoon, counted 4,000 dust particles in a cubic inch of the air, whereas 2 days before, in thick haze, he counted no fewer than 64,000 in the cubic inch. At Dumfries, the number counted on a very hazy day in October increased 20-fold over the number counted the day before when it was clear. All know that thick haze is usual in very sultry weather. The wavy, will-o'-the-wisp ripples near the horizon indicate its presence very plainly. During the intense heat there is generally much dust in the atmosphere. This dust, by the high temperature, attracts moisture from the apparently dry air, though above the saturation point. In all circumstances, then, the haze can be accounted for by the condensing power of the dust particles in the atmosphere, at a higher temperature than that required for the formation of fogs or mists or rain. End of Chapter 12, Haze. Recording by Pamela Krantz. Chapter 13 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 13. Hazing Effects of Atmospheric Dust. The transparency of the atmosphere is very much destroyed by the impurities communicated to it while passing over the inhabited areas of the country. Dr. Aitken devoted 18 months to compare the amount of dusty impurities in different masses of air, or of different airs brought in by winds from different directions. He took Falkirk for his center of observations. This town lies a little to the north of a line drawn between Edinburgh and Glasgow, and is nearly midway between them. If we draw a line due west from it and another due north, we find that in the northwest quadrant so enclosed, the population of that part of Scotland is extremely thin, the country over that area being chiefly mountainous. In all other directions the conditions are quite different. In the northeast quadrant are the fairly well-populated areas of Aberdeenshire, Forfarshire, and the thickly populated county of Fife. In the southeast quadrant are situated Edinburgh and the well-populated districts of the southeast of Scotland. And in the southwest quadrant are Glasgow and the large manufacturing towns which surround it. The winds from 3 of these quadrants bring air polluted in its passage over populated areas, whereas the winds from the northwest come comparatively pure. The general plan of estimating the amount of haze is to note the most distant hill that can be seen through the haze. The distance in miles of the farthest away hill visible is then called the limit of visibility of the air at the time. For the observations made at Falkirk, only 3 hills are available, one about 4 miles distant, the Ochils about 15 miles distant, and Ben Ledi about 25 miles distant, all in the northwest quadrant. When the air is thick, only the near hill can be seen, then the Ochils become visible as the air clears, and at last Ben Ledi is seen, when the haze becomes still less. After Ben Ledi is visible, it then becomes necessary to estimate the amount of haze on it, in order to get the limit of visibility of the air at the time. Thus, if Ben Ledi be half hazed, then the limit of visibility will be 50 miles. In this way, all the estimates of haze have been reduced to one scale for comparison. As the result of all the observations, it was found that as the dryness of the air increases, the limit of visibility also increases. A very marked difference in the transparency of the air was found with winds from the different directions. In the northwest quadrant, the winds made the air very clear, whereas winds from all other directions made the air very much hazed. The winds in the other 3 areas are nearly 10 times more hazed than those from the northwest quadrant. That is very striking. The conclusion come to is that the air from densely inhabited districts is so polluted that it is fully 9 times more hazed than the air that comes from the thinly inhabited districts. In other words, the atmosphere at Falkirk is about 10 times thicker when the wind is east or south than it would be if there were no fires and no inhabitants. It is interesting to notice that the limit varies considerably for the same wind at the same humidity. This is what might have been expected because from the observations made by the dust counter, the number of particles varied greatly in winds from the same directions, but at different times. This depends upon the rise and fall of the wind, changes in the state of trade, season of the year, and other causes. During a strike, the dearth of coal will make a considerable diminution in the number of dust particles in the air of large towns. With a north wind, the extreme limits of visibility are 120 to 200 miles, and with a northwest wind from 70 to 250 miles. An east wind has as limits 4 to 50 miles, and a southeast wind 2 to 60 miles. One interesting fact to be noticed after wading through these tables is this, that as a general result, the transparency of the air increases about 3.7 times for any increase in dryness from 2 degrees to 8 degrees of wet bulb depression. That is, the clearness of the air is inversely proportional to the relative humidity. Or put another way, if the air is 4 times drier, it is about 4 times clearer. End of Chapter 13. Hazing Effects of Atmospheric Dust. Recording by Pamela Krantz.
Chapter 14 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J.G. McPherson. Chapter 14. Thunder clears the air. The phrase thunder clears the air is familiar to all. It contains a very vital truth, yet even scientific men did not know its full meaning until just the other day. It came by experience to people who had been for ages observing the weather, and it is one of the most pointed of the weather lore expressions. Folks got to know, by a sort of rule of thumb, truths which scientifically they were unable to learn, and this is one. Perhaps, therefore, we should respect a little more what is called folklore, or ordinary people's sayings. Experience has taught men many wonderful things. In olden times they were keener natural observers. They had few books, but they had plenty of time. They studied the habits of animals and moods of nature, and they came wonderfully near to reaching the full truth, though they could not give a reason for it. The awe-inspiring in nature has especially riveted the attention of man, and no appearance in nature joins more powerfully the elements of grandeur and awe than a heavy thunderstorm. When suddenly, from the breast of a dark thundercloud, a brilliant flash of light darts zigzag to the earth, followed by a loud crackling noise which softens in the distance into weaker volumes of sound, terror seizes the birds of the air and the cattle in the field. The man who was born to rule the storm rejoices in the powerful display, but kings have trembled at the sight. Byron thus pictures a storm in the Alps. Far along, from peak to peak, the rattling crags among, leaps the live thunder, not from one lone cloud, but every mountain now hath found a tongue. And Jura answers through her misty shroud, back to the joyous Alps, who call to her aloud. Franklin found that lightning is just a kind of electricity. No one can tell how it is produced, yet a flash has been photographed. When the flash is from one cloud to another, there is sheet lightning, which is beautiful but not dangerous. But when the electricity passes from a cloud to the earth in a forked form, it is very dangerous indeed. The flash is instantaneous, but the sound of the thunder takes some time to travel. Roughly speaking, the sound takes 5 seconds, or 6 beats of the pulse, to the mile. All are now taught at school that it is the oxygen in the air which is necessary to keep us in life. If mice are put into a glass jar of pure oxygen gas, they will at once dance with exhilarating joy. It occurred to Sir Benjamin Richardson some time ago that it would be interesting to continue some experiments with animals and oxygen. He put a number of mice into a jar of pure oxygen for a time. They breathed in the gas and breathed out water vapor and carbonic acid. After the mice had continued this for some time, he removed them by an arrangement. By chemical means he removed the water vapor and carbonic acid from the mixed air in the vessel. When a blown-out taper was inserted, it at once burst into flame, showing that the remaining gas was oxygen. Again the mice were put into this vessel to breathe away. But strange to say, the animals soon became drowsy. The smartness of the oxygen was gone. At last they died. There was nothing in the gas to keep them in life. Yet by the ordinary chemical tests, it was still oxygen. It had repeatedly passed through the lungs of the mice, and during this passage there had been an action in the air cells which absorbed the life-giving element of the gas. It is oxygen so far as chemistry is concerned, but it has no life-giving power. It has been devitalized. But the startling discovery still remains. Sir Benjamin had previously fitted up the vessel with 2 short wires, opposite each other in the sides, part outside and part inside. The 2 wires are fastened to the outside knobs. These wires are attached to an electric machine, and a flash of electricity is made to pass between the inner points of the vessel. The wires are again removed. Nothing strange is seen in the vessel, but when living mice are put into the vessel, they dance as joyfully as if pure oxygen were in it. The oxygen in which the first mice died has now been quite refreshed by the electricity. The bad air has been cleared and made life-supporting by the electric discharge. It has been, again, vitalized. Now to apply this. Before a thunderstorm, everything has been so still for days that the oxygen in the air has been to some extent robbed of its life-sustaining power. This air feels close. A feeling of drowsiness comes over all. But after the air has been pierced by several flashes of lightning, the life force in the air is restored. Your spirits revive, you feel restored, your breathing is far freer, your drowsiness is gone. Then there is a burst of heavenly music from the exhilarated birds. Thus a thunderstorm clears the air. After the passage of lightning through the air, ozone is produced, the gas that is produced after a flash of electricity. It is a kind of oxygen, with fine exciting effects on the body. If then the life-sustaining power of oxygen depends on a trace of ozone, and this is being made by lightning's work, how pleased should we be at the occasional thunderstorm. End of Chapter 14. Recording by Amy Graymore. amysmindtoyourmind.com.
Chapter 15 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick Wells. Meteorology by J.G. McPherson. Chapter 15. Disease Germs in the Air. The gay motes that dance in the sunbeams are not all harmless. All are annoying to the tidy housekeeper, but some are dangerous. There are living particles that float in the air as the messengers of disease and death. Some, falling on fresh wounds, find there a suitable feeding place, and, if not destroyed, generate the deadly influence. Others are drawn in with the breath, and, unless the lungs can withstand them, they seize hold and spread some sickness or disease. From stagnant pools, common sewers, and filthy rooms, disease germs are constantly contaminating the air. Yet these can be counted. The simplest method is that of Professor Frankland. It depends on this principle. A certain quantity of air is drawn through some cotton wool. This wool seizes the organisms as the air passes through. These organisms are afterward allowed to feed upon a suitable nutritive medium until they reach maturity. They are then counted easily. About an inch from one end of a glass tube, 5 inches long and 1 inch bore. The glass is pressed in during the process of blowing. Some cotton wool is squeezed in to form a plug at the farther constricted part of the glass. The important plug is now inserted at the same open end, but is not allowed to go beyond the constricted part at its end. A piece of long lead tubing is attached to the former end by an India rubber tube. The other end of the lead tubing is connected with an exhausting syringe. 60 strokes of the 18 cubic inches syringe will draw 1,080 cubic inches of air to be examined through the plugs, the first retaining the organism. The impregnated plug is then put into a flask containing in solution some gelatin peptone. The flask is made to revolve horizontally until an almost perfectly even film of gelatin and the organisms from the broken up plug cover its inner surface. The flask is allowed to remain for an hour in a cool place, and is then placed under a jar bell at a temperature of 70 degrees Fahrenheit. There it remains to allow the germs to incubate for 4 or 5 days. The surface of the flask having been previously divided into equal parts by ink lines, the counting is now commenced. If the average be taken for each segment, the number of the whole is easily ascertained. A simple arithmetical calculation then determines the number of organisms in a cubic foot, since the number is known for the 1,080 cubic inches. This is the process for determining the number of living organisms in a fixed quantity of air. No less than 30 colonies of organisms were counted in a cubic foot of air taken from the Golden Gallery of St. Paul's Cathedral, London, and 140 from the air of the churchyard. An ordinary man would breathe there 36 microorganisms every minute. Electricity has a powerful effect in destroying these organisms. Ozone is generated in the air by lightning, and it is detrimental to them. In fine ozoned highland air, scarcely a disease germ can be detected. Open sea air contains about 1 germ in 2 cubic feet. It has been found that in Paris, the average number in summer is about 140 per cubic foot of air, but in bedrooms the number is double. During the 24 hours of the day, the number of germs is highest about 6 a.m. and lowest about midday. Raindrops carry germs to the ground. hence the advantage of a thunderplout in a sanitary way. A cubic foot of rain has been found to contain 5,500 organic dust germs, besides the 7 billion of inorganic dust particles. In a dirty town, the rain will bring down in a year, upon a square foot of surface, no less than 3 million of bacteria, many of them being disease-bearing and death-bearing. No wonder, then, that scientific men are using every endeavor to protect the human frame, as well as the frame of the lower animals, from the baneful inroads of these floating nuclei of disease and death. End of chapter 15.
Chapter 16 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick Wells. Meteorology by J.G. McPherson. Chapter 16. A Change of Air. For weakness of body and fatigue of mind, a very common and essentially serviceable recommendation is a change of air. Of course, the change of scene from coast to country or from town to hillside may help much the depressed in body or mind, and this is very commendable. But strange to say, there is a healing virtue in breathing different air. At first, one is apt to think that air is the same all over, as he thinks water is, especially outside smoky towns, but both have varied qualities in different parts. You have only to be assured that in a cubic inch of bedroom air, in the denser part of a large town, there are about 20 million dust particles, and in the open air of a heathery mountainside, there are only some hundreds, to see that there is something, after all, on the face of it in the old wives' tale. Not that the dust particles are all injurious, for most of them are inorganic, and many of the organic particles are quite wholesome, yet there is a change wrought, often very marked, in going from one place to another for different air. Even in the country, especially in summer-time, one distinctly notices the great differences in the air of lowland and highland localities. The 10-mile change from Strathmore to Glenisla shows a marked difference in the air. Below, it is close, weakening, enervating. Above, it is exhilarating, invigorating, and strong. Some people must have a change, at least those who can afford it, for health must be seen to first of all, if one have means to do so. Oh, the blessing of good health! How many who enjoy it never think of the misery of its loss. In fact, health is the soul that animates all enjoyments of life, for without it those would soon be tasteless. A man starves at the best spread table, and is poor in the midst of the greatest treasures without health. In these days, half of our diseases come from the neglect of the body in the overwork of the brain. The wear and tear of labor and intellect go on without pause or self-pity. Men may live as long as their forefathers, but they suffer more from 1,000 artificial anxieties and cares. The men of old fatigued only the muscles, we exhaust the inner strength of the nerves. Even more so now, then, do we require a change of air to soothe our overwrought nervous system. And when that magic power, concealed from mortal view, works such wonders on the health, surely it is one's duty to save up and have it, when it is within one's means. For is not health the greatest of all possessions? What a rich color clothes the countenance of the young after a month's outing in the hill country! How fine and pure has the blood become! All stagnant humors, accumulated in wintry town life, have been dispelled by the ozone-brightening charm. The weary-looking office or shop man is now transfigured into a sprightly youth once more, ready with strong recuperated power for another winter's labors. The pale wife, who has been stifled for months in close-aired rooms, has now a healthy flush on her becoming countenance that speaks of gladly restored health, and all this has been brought about by a change in air. For a thorough change to a town man, he should make for the highlands. There he is never tired of walking, for the air which he breathes is full of ozone. This revivifying element in the air is produced by the lightning bursts from hill to hill. There is in the highlands a continual rush of electricity, whether seen or not. Hence the air is very pure, free from organic germs, intensely exhilarating and buoyant. Sportsmen are livingly aware of the recuperating power of high air. Perhaps these city men do not benefit so much by the easy walking exercise on the grouse moors as in breathing the splendidly delight-inspiring air. What a change one feels there in a very few hours! A change in air is an old wives' adage, but much of the weather lore of our forefathers was based on real scientific principles only now coming to light. Nature is ever true, but it requires patience to unravel her secrets. We therefore advocate an occasional change in air to improve the health. The chiefest good, bestowed by heaven, but seldom understood. End of chapter 16.
Chapter 17 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avaí in April 2012. Meteorology by J.G. McPherson. Chapter 17. The Old Moon in the New Moon's Arms. After the sun's broad beams have tired the sight, the moon with more sober light charms us to descry her beauty, as she shines sublimely in her virgin modesty. There is always a most fascinating freshness in the first sight of the new moon. The superstition of centuries adds to this charm. Why boys and girls like to turn over a coin in their pocket at this sight, one cannot tell, yet it is done. No young lady likes to look at the new moon through a pane of glass, and farmers are always confident of a change of weather with a new moon. At least in bad weather they earnestly hope for it. But, banishing all superstition, we welcome the pale silver sickle in the heavens, once more appearing from the bosom of the azure. And no language can equal these beautiful words of the youthful Shelley. Like the young moon, when on the sunlit limits of the night her white shell trembles amid crimson air, and while the sleeping tempest gathers might, doth, as the herald of his coming, bear the ghost of his dead mother, whose dim form bends in dark ether from her infant's chair. That is a more charming way of putting the ordinary expression, the old moon in the new moon's arms. We are regularly accustomed to the moonshine, but only occasionally is the earth's shine on the moon so regulated that the shadowed part is visible. This is not seen at the appearance of every new moon. It depends upon the positions of the sun and moon, the state of the atmosphere, and the absence of heavy clouds. I never in my life saw the phenomenon so marvellously beautiful as on May 7th, 1894, at my manse in Strathmore. I took particular note of it, as some exceedingly curious things were connected with it. At 9 o'clock in the evening, the new moon issued from some clouds in the western heavens, the sun having set about an hour before. The crescent was thin and silvery, and the outline of the shadowed part was just visible. The sky near the horizon was clear and greenish-hued. As the night advanced, the moon descended, and at 10 o'clock she was approaching a purple stratum of clouds that stretched over the hills, while the position of the sun was only known a little to the east by the back-thrown light upon the dim sky. Through the moisture-laden air the sun's rays, reflected by the moon, threw a golden stream from the crescent moon, for the silvery shell became more golden-hued. The horns of the moon now seemed to project, and the shadowed part became more distinct, through the circle appeared smaller. By means of a field-glass I noticed that this was extra-lighted, with points here and there quite golden-tinged. The darker spots showed the deep caverns, The brighter points brought into relief the mountain peaks. Why was the surface brighter than usual? I cannot go into detail about the phases of the moon, but in a word I may say that, while the sun can illuminate the side of the moon turned towards it, it is unable to throw any light on the shadow, seeing that there is no atmosphere around the moon to reflect the light. If we, in imagination, looked from the moon upon the earth, we should see the same phases as are now noticed in the moon, and when it is just before new moon on the earth will appear fully illuminated from the moon. We would also observe, from the moon, that the brightness of the illuminated part of the earth would vary from time to time, according to the changes in the earth's atmosphere. More light would be reflected to the moon from the clouds in our atmosphere than from the bare earth or cloudless sea, since clouds reflect more light than either land or sea. Accordingly, we arrive at this curious fact, that the extra brightness of the dark body of the moon is mainly determined by the amount of cloud in our atmosphere. Accordingly, I concluded that there must be clouds to the west, though I could not see them, which reflected rays of light and faintly illuminated the shadowed part of the moon. It had become much colder, and I concluded that during the night the cloud particles, if driven near by the wind, would condense into rain. And assuredly, next morning I was gratified to find that rain had fallen in large quantities, substantiating the theory. There is much pleasure in verifying such an interesting problem. The dark body of the moon being more than usually visible is one of our well-known and oldest indications of coming bad weather. And at once came to my memory the lines of Sir Patrick Spens as he foreboded rain for his crossing the North Sea. I saw the new moon late yestreen, with the old moon in her arm, and if we gang to sea, master, I fear will come to harm. This lunar indication, then, has a sound physical basis, showing that near the observer there are vast areas of clouds which are reflecting light upon the moon at the time, before they condense into rain by the chilling of the air. According to the old Greek poet, Aratus, if the new moon is ruddy and you can trace the shadow of the complete circle, a storm is approaching. End of chapter 17.
Chapter 18 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J. G. McPherson. Chapter 18. An Autumn Afterglow. A brilliant afterglow is welcomed for its surpassing beauty and a precursor of fine fixed weather. A glorious sunset has always had a charm for the lover of nature's beauties. The zenith spreads its canopy of sapphire, and not a breath creeps through the rosy air. A magnificent array of clouds of numberless shapes comes smartly into view. Some far off are voyaging their sun-bright paths in silvery folds, others float in golden groups. Some masses are embroidered with burning crimson, others are like islands all lovely in an emerald sea. Over the glowing sky are splendid colorings. The flood of rosy light looks as if a great conflagration were below the horizon. I remember witnessing an especially brilliant sunset last autumn on the high road between Kirriemuir and Blairgowrie. The setting sun shone upon the back of certain long trailing clouds, which were much nearer me than a range behind. The fringes of the front range were brilliantly golden, while the face of those behind was sparklingly bright. Then the sun disappeared over the western hills, and his place was full of spokes of living light. Looking eastward, I observed on the horizon the base of the northern line of a beautiful rainbow, the shepherd's delight for fine weather. Soon in the west the light faded, but there came out of the east a lovely flush, and the general sky was presently flamboyant with afterglow. The front set of clouds was darker except on the edges, the red being on the clouds behind, and the horizon in the east was particularly rich with dark red hues. Gradually the eastern glow rose and reddened all the clouds, but the front clouds were still gray. The effect was very fine in contrast. The fleecy clouds overhead became transparently light red as they stretched over to reach the silver-streaked west. The new moon was just appearing upright against a slightly less bright opening in the sky, betokening the firm hardness of autumn. Soon the coloring melted away, and the peaceful reign of the later twilight possessed the land. Now, why that brilliancy of the east when the west was colorless? Most of all, you note the immense variety and wealth of reds. These are due to dust in the atmosphere. We are the more convinced of this by the very remarkable and beautiful sunsets which occurred after the tremendous eruption at Krakatoa in the Straits of Sunda 30 years ago. There was then ejected an enormous quantity of fine dust, which spread over the whole world's atmosphere. So long as that vast amount of dust remained in the air did the sunsets and afterglows display an exceptional wealth of coloring. All observers were struck with the vividly brilliant red colors in all shades and tints. The minute particles of dust in the atmosphere arrest the sun's rays and scatter them in all directions. They are so small, however, that they cannot reflect and scatter all. Their power is limited to the scattering of the rays at the blue end of the spectrum, while the red rays pass on unarrested. The display of the colors of the blue end are found in numberless shades, from the full deep blue in the zenith to the greenish blue near the horizon. If there were no fine dust particles in the upper strata, the sunset effect would be whiter. If there were no large dust particles, there would be no coloring at all. If there were no dust particles in the air at all, the light would simply pass through into space without revealing itself. And the moment the sun disappeared, there would be total darkness. The very existence of our twilight depends on the dust in the air, and its length depends on the amount and extension upwards of the dust particles. But how have the particles been increased in size in the east? Because as the sun was sinking, but before its rays failed to illumine the heavens, the temperature of the air began to fall. This cooling made the dust particles seize the water vapor to form haze particles of a larger size. The particles in the east first lose the sun's heat and first become cool, and the rays of light are then best sifted, producing a more distinct and darker red. As the sun dipped lower, the particles overhead became a turn larger, and thereby better reflected the red rays. Accordingly, the roseate bands in the east spread over to the zenith and passed over to the west, producing in a few minutes a universal transformation glow. To produce the full effect often witnessed, there must be, besides the ordinary dust particles, small crystals floating in the air, which increase the reflection from their surfaces and enhance the glow effects. In autumn, after sunset, the water-covered dust particles become frozen, and the red light streams with rare brilliancy, causing all reddish and colored objects to glow with a rare brightness. Then the air glows with a strange light as of the northern dawn. From all this it is clear that though the coloring of sunset is produced by the direct rays of the sun, the afterglow is produced by reflection, or rather radiation from the illuminated particles near the horizon. The effect in autumn is a stream of red light, of varied tones, and rare brilliancy in all quarters, unseen during the warmer summer. We have to witness the sunsets at Ballachulish to be assured that Waller Paton really imitated nature in the characteristic bronze tints of his richly painted landscapes. End of Chapter 18. An Autumn Afterglow. Recording by Pamela Krantz.
Chapter 19 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Gonzalez. Meteorology by J.G. McPherson. Chapter 19. A Winter Foreglow. Little attention has been paid to foreglows compared with afterglows, either with regard to their natural beauty or their weather forecasting. The either the ordinary cloud surroundings at sunrise, or the western foreglow at rarer intervals betokens to the weather prophet wet and gloomy weather. The farmer and the sailor do not like the sight. It depends so much on the favourable weather conditions. Of course, sunrise to the aesthetic observer has always its charms. The powerful king of day rejoices as the bridegroom coming out of his chamber, as he steps upon the earth over the dewy mountain tops, bathing all in light, and spreading gladness and deep joy before him. The lessening cloud, the kindling azure, and the mountain's brow illumined with golden streaks, mark his approach. His encompassed with bright beams as he throws his unutterable love for the clouds. The beauteous robes of heaven, as land the dew-bright earth and coloured air. He looks in boundless majesty abroad, touching the green leaves all a-tremble with gold light. The glorious and educating and inspiring as is the sunrise in itself in many cases, there is occasionally something very remarkable that is connected with it. Rare is it, but how charming a witness that till very recently was all but unexplained. This is a foreglow. It is in no respect so splendid as afterglow succeeding sunset, but, with its comparative rarity, its beauty is enhanced. I remember a foreglow most vividly, which was seen at my manse in Strathmore, in January 1893. My bedroom window looked due west. I slept with blind up. On that morning I was struck, just after the darkness was fading away, with a slight colouring all along the western horizon. The skeleton branches of the trees stood out strongly against it. The colouring gradually increased, and the roseate hue stretched higher. The well-known phases that I used to conjure up out of the thin blended buffs became more lifelike, as the cheeks flushed. There was rare warmth in a winter morning to cheer the half-despairing soul, tired of the long hours of all-reading, and pierced to the heart by never-ceasing rhymes, yet I could not understand it. I went to the room opposite to watch the sunrise, for I had observed in the diary that the appearance of the sun would not be for a few minutes. There were streaks of light in the east above the horizon, when no colour was visible. The hectic flush slight, yet well marked, which was deepening in the western heavens, had no counterpart in the east, except the colourless light which marked the wintry sun's near approach. As soon as the sun's rays shut up the eastern clouds, and his orbs appeared above the horizon, the western sky paled, the colour left it, as if ashamed of its assumed glory. A foreglow like that I have rarely seen, and its existence was a puzzle to me till I studied Dr. Aitken's explanation of the afterglows after sunset. I had never come across any description of a foreglow, and of course across no explanation of the curious phenomenon. The western heavens were so coloured with fair brightly roseate hues, while the eastern horizon was only silvery bright before the sun rose, whereas after the sun appeared and coloured the eastern hills and clouds, the western sky was a misleading grey and colourless appearance. Why was that? What is the explanation? I have not space enough to repeat the explanation given already in the last chapter of the glorious phenomena of the afterglow, but the explanation is similar. Before sunrise, the rays of the sun are reflected by dust particles in the zenith to the western clouds. The colouring is intensified by the frozen water vapour on these particles in the west. One thing I carefully noted: ere midday, snow began to fall, and for some days a severe snowstorm kept us indoors. Then, at any rate, the foreglow betokened a coming storm. It was, like a rainbow in a summer morning, a decided warning of the approaching wet weather. End of Chapter 19. Recording by April Gonzalez in Cavite, Philippines.
Chapter 20 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in February 2012. Meteorology by J.G. McPherson. Chapter 20. The Rainbow. The poet Wordsworth rapturously exclaimed, "My heart leaps up when I behold a rainbow in the sky." And old and young have always been enchanted with the beautiful phenomenon. How glorious is the party-colored girdle which, on an April morning or September evening, is cast o'er mountain, tower, and town, or even mirrored in the ocean's depths. No colors are so vividly bright as when this triumphal arch bespans a dark nimbus. Then it unfolds them in due prismatic proportion, running from the red to where the violet fades into the sky. A plain description of the formation of the rainbow is not very easily given, but a short sketch may be useful. Beautiful as is the ethereal bow, born of the shower and colored by the sun, yet the marvelous effect is more exquisitely intensified in its gorgeous display when the hand of science points out the path in which the sun's rays, from above the western horizon, fall on the watery cloud, indicating fine weather, the shepherd's delight. One law of reflection is that, when a ray of light falls on a plane or spherical surface, it goes off at the same angle to the surface as it fell. One law of refraction is that when a ray of light passes through one medium and enters a denser medium, as from air to water, it is bent back a little. By refraction you see the sun's rays long after the sun has set. When the sun is just below the horizon, an observer, on the surface of the earth, will see it raised by an amount which is generally equal to its apparent diameter. The rays of different colors are bent back, when passing through the water, at different rates, some slightly, others more, from the red to the violet end. The rainbow, then, is produced by refraction and reflection of the several colored rays of sunlight in the drops of water which make up falling rain. The sun is behind the observer, and its rays fall in a parallel direction upon the drops of rain before him. In each drop the light is dispersively refracted, and then reflected from the farther face of the drop. It travels back through the drop and comes out with dispersing colors. According to the height of the sun or the slope of its rays, a higher or lower rainbow will be formed. And, strange, no two people can see the very same bow. In fact, the rainbow, as seen by the one eye, is not formed by the same water drops as the rainbow seen by the other eye. When the primary bow is seen in most vivid colors on a dark cloud, a second arch, larger and fainter, is often seen. But the order of the colors is quite reversed. At a greater elevation, the sun's ray enters the lower side of a drop of rainwater, is refracted, reflected twice, and then refracted again before being sent out to the observer's eye. That is why the colors are reversed. A one-colored rainbow is a curious and rare phenomenon. It is a strange paradox, for the very idea of a rainbow brings up the 7 colors: red, orange, yellow, green, blue, indigo, and violet. Yet Dr. Aitken tells us of a rainbow with one color which he observed on Christmas Day in 1888. He was taking his walk on the high ground south of Falkirk. In the east he observed a strange pillar-like cloud lit up with the light of the setting sun. Then the red pillar extended, curved over, and formed a perfect arch across the northeastern sky. When fully developed, this rainbow was the most extraordinary one which he had ever seen. There was no color in it but red. It consisted simply of a red arch, and even the red had a sameness about it. Outside the rainbow there was part of a secondary bow. The Ochil Hills were north of his point of observation. These hills were covered with snow, and the setting sun was glowing with rosy light. Never had he seen such a depth of color as was on them on this occasion. It was a deep, furnacy red. The sun's light was shorn of all the rays of short-wave light on its passage through the atmosphere, and only the red rays reached the earth. The reason why the Ochils glowed with so deep a red was owing to their being overhung by a dense curtain of clouds which screened off the light of the sky. The illumination was thus principally that of the direct softer light of the sun. End of chapter 20. Chapter 21 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in February 2012. Meteorology by J.G. McPherson. Chapter 21. The Aurora Borealis. He must be a very careless observer who has not been struck with the appearance of the streamers which occasionally light up the northern heavens, and which farmers consider to be indicators of strong wind or broken weather. The time was when the phenomenon was considered to be supernatural and portentous, as the chroniclers of spectral battles, when fierce, fiery warriors fought upon the clouds in ranks and squadrons and right form of war. And even in the rural districts of Britain, the blood-colored aurora of October 24, 1870, was considered to be the reflection of an enormous Prussian bonfire, fed by the beleaguered French capital. In joyful spirit, the Shetlanders call the beautiful natural phenomenon merry dancers. Burns associated their evanescence with the transitoriness of sensuous gratification. They flit ere you can point their place. And Tennyson spoke of his cousin's face lit up with the color and light of love, as I have seen the rosy red flushing in the northern light. Yet this phenomenon is to a great extent under the control of cosmical laws. One of the most difficult problems of our day has been to disentangle the irregular webwork of aurorae and bring them under a law of periodicity, which depends upon the fluctuations of the sun's photosphere and the variations on the earth's magnetism, and which have such an important influence upon the fluctuations of the weather. The name Aurora Borealis was given to it by Gassendi in 1621. Afterwards, the old almanacs described it as the great amazing light in the north. In the lowlands of Scotland, the name it long went by of Lord Derwentwater's lights was given because it suddenly appeared on the night before the execution of the rebel lord. In Ceylon, aurorae were called Buddha lights. The first symptom of an aurora borealis is commonly a low arch of pale greenish-yellow light, placed at right angles to the magnetic meridian. Sometimes rays cover the whole sky, frequently showing tremulous motion from end to end, and sometimes they appear to hang from the sky like the fringes of a mantle. They are among the most capricious of natural phenomena, so full of individualities and vagaries. To the glitter of rapid movement they add the charm of vivid coloring. It is strongly asserted that aurorae are preceded by the same general phenomena as thunderstorms. This was borne out by Piazzi Smith, late Astronomer Royal for Scotland, who observed that their monthly frequency varies inversely with that of thunderstorms, both being safety valves for the discharge of surplus electricity. Careful observers have, moreover, noticed a remarkable coincidence between the display of aurorae and the maxima of the sun's spots and of the earth's magnetic disturbances. Some have supposed that the light of the aurora is caused by clouds of meteoric dust, composed of iron, which is ignited by friction with the atmosphere. But there is this difficulty in the way. Shooting stars are more frequent in the morning, while the reverse is the case with the aurora. The highest authorities have concluded, pretty uniformly, that aurorae are electric discharges through highly rarefied air, taking place in a magnetic field and under the sway of the Earth's magnetic induction. They are not inappropriately called polar lightnings, for when electricity misses the one channel, it must traverse the other. The natives of the Arctic regions of North America pretend to foretell wind by the rapidity of the motions of the streamers. When they spread over the whole sky in a uniform sheet of light, fine weather ensures. Fitzroy believed that aurorae in northern latitudes indicated and accompanied stormy weather at a distance. The same idea is still current among many farmers and fishermen in Scotland. Is there any audible accompaniment to the brilliant spectacle? The natives of some parts with subtle hearing power speak of the whizzing sound which is often heard during auroral displays. Burns tells of their hissing, eerie din as echoes of the far-off songs of the Valkyries. Perhaps the most striking incident which corroborates this opinion occurred during the Franco-Prussian War. Rollier, a practice aeronaut, left Paris in a balloon on his mission of city defense, and 14 hours afterward landed in Norway. He had reached a height of 2.5 miles. When descending, he passed through a peculiar cloud of sulphurous odor which emitted flashed light and a slight scratching or rustling noise. On landing, he witnessed a splendid Aurora Borealis. He must, therefore, have passed through a cloud in which an electrical discharge of an auroral nature was proceeding, accompanied with an audible sound. There is, moreover, no improbability of such sounds being occasionally heard, since a somewhat similar phenomenon accompanies the brush discharge of the electric machinery, to which the aurora bears considerable resemblance. Though no fixed conclusions are yet established about the causes of the brilliant auroral display, yet, as the results of laborious observations, we are assured that the stabler center of our solar system holds in its powerful sway the several planets at their respective distances, supplying them all with their reasonable light and heat, vibrating sympathetic chords in all, and even controlling under certain, though to us still unknown, laws the electric streamers that flit, apparently lawlessly, in the distant Earth's atmosphere. End of chapter 21.
Chapter 22 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J. G. McPherson. Chapter 22, The Blue Sky. If we look at the sky overhead, when cloudless in the sunshine, we wonder what gives the air such a deep blue color. We are not looking, as children seem to do, into vacancy, away into the far unknown. And even if that were the case, would not the space be quite colorless? What then produces the blueness? Some of the very fine dust particles, even when clothed with an exceedingly thin coating of water vapor, are carried very high. And looking through a vast accumulation of these, we find the effect of a deep blue color. Why so? Because these particles are so small that they can only reflect the rays of the blue end of the spectrum, and the higher we ascend, the smaller are the particles and the deeper is the blue. But it is also because water, even in its very finest and purest form, is blue in color. For long this was disputed. Even Sir Robert Christison concluded, after years of experimenting on highland streams, that water was colorless. Of course, he admitted that the water in the Indian and Pacific Oceans has frequent patches of red, brown, or white color, from the myriads of animalcules suspended in the water. Ehrenberg found that it was vegetable matter which gave to the Red Sea its characteristic name, but these and similar waters are not pure. It is to Dr. Aitken that the final discovery of the real color of water is due. When on a visit to several towns on the shores of the Mediterranean, he set about making some very interesting experiments, which the reader will follow with pleasure. It is a well-known fact that color transmitted through different bodies differs considerably from color reflected by them. In his first experiment he took a long empty metal tube, open at one end, and closed at the other end by a clear glass plate. This was let down vertically into the water, near to a fixed object, which appeared of most beautiful deep and delicate blue at a depth of 20 feet. Scientific men know that if the color of water is due to the light reflected by extremely small particles of matter suspended in the water, then the object looked at through it would have been illuminated with yellow, the complementary color of blue. A blackened tube was then filled with water, which had a clear glass plate fixed to the bottom, and white, red, yellow, and purple objects were sunk in the water, and these colors were found to change in the same way as if they were looked at through a piece of pale blue glass. The white object appeared blue, the red darkened very rapidly as it sank, and soon lost its color. At the depth of 7 feet, a very brilliant red was so darkened as to appear dark brick red. The yellow object changed to green, and the purple to dark blue. But, still further to satisfy himself that water is really blue in itself, even without any particles suspended in it, he tested the color of distilled water. He filled a darkened tube with this water, clear glass plates being at the ends of the tube, and looked through it at a white surface. The effect was the same as before. The color was blue, almost exactly of the same hue as a solution of Prussian blue. This is corroborated by the fact that the purer the water is in nature, the bluer is the tint when a large quantity is looked through. Some Highland lochs have crystal waters of the most extraordinary blue. Of course, some cling to the old idea that this is accounted for by the reflected blue of the clear heavens above. No doubt, if the sky be deep blue, then this blue light, when reflected by the surface of the water, will enrich and deepen the hue, but the water itself is really blue. At the same time, the dust particles suspended in the water have a great effect in making the water appear more beautiful, brilliant, and varied in its coloring, because little or no light is reflected by the interior of a mass of water itself. If a dark metal vessel be filled with a weak solution of Prussian blue, the liquid will appear quite dark and void of color. But throw in some fine white powder, and the liquid will at once become of a brilliant blue color. This accounts for the change of depth and brilliancy of color in the several shores of the Mediterranean. When, then, you look at the face of a deep blue lake on a summer evening, the heavens all aglow with the unrivaled display of color from the zenith, stretching in lighter hues of glory to the horizon, though to you the calm water appears like a lake of molten metal, glowing with sky-reflected light, so powerful and brilliant as entirely to overpower the light which is internally reflected, yet blue is the normal color of the water. Blueness is its inherent hue. Looking upwards, we observe 3 distinct kinds of blue in the sky from the horizon to the zenith. All painters in watercolors know that. Newton thought that the color of the sky was produced in the same way as the colors in thin plates, the order of succession of the colors gradually increasing in intensity. End of Chapter 22. The Blue Sky. Recording by Pamela Krantz. Chapter 23 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 23. A Sanitary Detective. The impure state of the air in the rooms of a house can now be determined by means of color alone. Dr. Aitken has invented a very simple instrument for that purpose, and this ought to be of great service to sanitary officers. It is called the conoscope, or dust detective. The instrument consists of an air pump and a metal tube with glass ends. Near one end of the test tube is a passage by which it communicates with the air pump, and near the other end is attached a stopcock for admitting the air to be tested. It is not nearly so accurate as the dust counter, but it is cheaper, more easily wrought, and more handy for quick work. All the grades of blue, from what is scarcely visible to deep dark blue, may be attached alongside the tube on pieces of colored glass, and opposite these colors are the numbers of dust particles in the cubic inch of the similar air, as determined by the dust counter. While the number of particles was counted by means of the dust counter, the depth of blue given by the conoscope was noted, and the piece of glass of that exact depth of blue attached. A metal tube was fitted up vertically in the room in such a way that it could be raised to any desired height into the impure air near the ceiling, so that supplies of air of different degrees of impurity might be obtained. To produce the impurity, the gas was lit and kept burning during the experiments. The air was drawn down through the pipe by means of the air pump of the conoscope, and it passed through the measuring apparatus of the dust counter on its way to the conoscope. It may be remarked that by a stroke of the air pump, the air within the test tube is rarefied, and the dust particles seize the moisture in the supersaturated air to form fog particles. Through this fog, the color is observed, and the shade of color determines the number of dust particles in the air. These colors are named just visible, very pale blue, fine blue, deep blue, and very deep blue. When making a sanitary inspection, the pure air should be examined first, and the color corresponding to that should be considered as the normal health color. Any increase from the depths would indicate that the air was being gradually contaminated, and the amount of increase in the depth of color would indicate the amount of increase of pollution. As an illustration of what this instrument can detect, a room of 24 by 17 by 13 feet was selected. The air was examined before the gas was lighted, and the color in the test tube was very faint, indicating a clear atmosphere. In all parts of the room this was found the same. A small tube was attached to the test tube, open at the other end, for taking air from different parts of the room. 3 jets of gas were then lit in the center of the room, and observations at once begun with the conoscope. Within 35 seconds of striking the match to light the gas, the products of combustion had extended near the ceiling to the end of the room. This was indicated by the color in the conoscope, suddenly becoming a deep blue. In 4 minutes, the deep blue producing air was got at a distance of 2 feet from the ceiling. In 10 minutes, there was strong evidence of the pollution all through the room. In half an hour, the impurity at 9 feet from the floor was very great, the color being an intensely deep blue. The wide range of the indications of the instrument, from pure clearness to nearly black blue, makes the estimate of the impurity very easily taken with it, and as there are few parts to get out of order, it is hoped it may come into general use for sanitary work. End of Chapter 23, A Sanitary Detective. Recording by Pamela Krantz.
Chapter 24 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J.G. McPherson. Chapter 24. Fog and Smoke. Just 240 years ago, Mr. John Evelyn, F.R.S., a well-known writer on meteorology, sent a curious tract to King Charles II, which he was ordered to be printed by His Majesty. It was entitled Fumifugium, and dealt with the great smoke nuisance in London. I find from the thesis that he had a very hazy idea of the connection between fog and smoke, and no wonder, for it is only lately that the connection has been fully explained. We know that without dust particles there can be no fog, and that smoke supplies a vast amount of such particles. Therefore, in certain states of the atmosphere, the more smoke, the more fog. In Mr. Evelyn's day, the fog, which he called presumptuous smoke, was at times so dense that men could hardly discern each other for the cloud. His Majesty's only sister had complained of the damage done to her lungs by the contamination, and Mr. Evelyn was disgusted at the apathy of the people to do anything to remedy the nuisance. He deplored that the glorious and ancient city of London should wrap her stately head in clouds of smoke, so full of stink and darkness. He was of opinion that a method of charring coal so as to divest it of its smoke, while leaving it serviceable for many purposes, should be made the object of a very strict inquiry. And he was right, for it is now known that fog in a town is intensified by much smoke. In a city like London or Glasgow, where a great river, fed by warm streams of water from gigantic works, passes through its center, fogs can never be entirely obliterated, for the dust particles in the air, often 4 millions and upwards in the cubic inch, will seize with terrible avidity the warm vapor rising from the river. That is the main reason why fogs cannot there be put down. Smoke is being consumed to a great extent, yet we find particles of sulfur remaining, which seize the warm vapor and form fogs dense enough to check all traffic. The worst form of city fog seems to be produced when the air, at first flowing slowly in one direction, then turns on its tracks and flows back over the city, bringing with it a black pall, the accumulated products of previous days, to which gets added the smoke and other impurities produced at the time. What irritated Mr. Evelyn was that, outside of London, the air was clear when passengers could not walk in safety within the limits. So vexed was he about the contamination, that he made it the occasion of all the cathars, phthisis, coughs, and consumption in the city. He appealed to common sense to testify that those who repair to London soon take some serious illness. I know a man, he said, who came up to London and took a great cold, which he could never afterwards claw off again. Mr. Evelyn proposed that, by an Act of Parliament, the nuisance be removed, enjoining that all breweries, dye works, soap and salt boilers, lime burners, and the like be removed 5 or 6 miles distant from London, below the River Thames. That would have materially helped his cause. But there was more difficulty in the purification than he anticipated, yet there was pluck in the old man pointing out the killing contamination and suggesting a possible remedy. He had the fond idea that thereby a certain charm, or innocent magic, would make a transformation scene like Arabia, which is therefore styled the happy, attracting all with its gums and precious spices. In purer air, fogs would be less dense, breathing would be easier, business would be livelier, life would be happier. Few, I suppose, have laid their hands on this curious Latin thesis, or its quaint translation, directing the king's attention to the fogs that were ruining London. Since that time, the city has increased from little more than a village to be the dwelling place of 6 million of human beings. Yet too little improvement has been made in the removal of this fog nuisance. King Edward's drive through London would be even more dangerous on a muggy, frosty day than was Charles II's when science was little known. End of chapter 24. Chapter 25 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick Wells. Meteorology by J.G. McPherson. Chapter 25. Electrical Deposition of Smoke. A good deal of scientific work is being done in the way of clearing away fog and smoke, and this, through time, may have some practical results in removing a great source of annoyance, illness, and danger in large towns. Sir Oliver Lodge and Dr. Aitken have been throwing light upon the deposition of smoke in the air by means of electricity. If an electric discharge be passed through a jar containing the smoke from burnt magnesium wire, tobacco, brown paper, and other substances, the dust will be deposited so as to make the air clear. Brush discharge, or anything that electrifies the air itself, is the most expeditious. If water be forced upward through a vertical tube, with the nozzle 1/20th of an inch in diameter, it will fall to the ground in a fine rain, but if a piece of rubbed, electrified, sealing wax be held a yard distant from the place where the jet breaks into drops, they at once fall into large spots, as in a thunder shower. If paper be put on the ground during the experiment, the sound of pattering rain will be observed to be quite different. If a kite be flown into a cloud and made to give off electricity for some time, the clouds will begin to condense into rain. Experiments with Lord Kelvin's recorder show that variations in the electrical state of the atmosphere precede a change in weather. Then, with a very large voltaic battery, a tremendous quantity of electricity could be poured into the atmosphere, and its electrical condition could be certainly disturbed. If this could be made practically available, how useful it would be to farmers when the crops were suffering from excessive drought. It might be more powerfully available than the imagined condensation of a cloud into rain by the reverberation caused by the firing of a range of cannon. But what is the practical benefit of this information? If electricity deposits smoke, it might be made available in many ways. The fumes from chemical works might be condensed, and the air in large cities, otherwise polluted, might be purified and rendered innocuous. The smoke of chimneys in manufacturing works might be prevented from entering the atmosphere at all. In flour mills and coal mines, the fine dust is dangerously explosive. In lead, copper, and arsenic works, it is both poisonous and valuable. Lead smelters labor under this difficulty of condensing the fume which escapes along with the smoke from red lead smelting furnaces, and it was considered that an electrical process of condensation might be made serviceable for the purpose. At Bagilt, the method used for collecting and condensing the lead fume is a large flue 2 miles long. Much is retained in this flue, but still a visible cloud of white lead fume continually escapes from the top of the chimney. There is a difficulty in the way of depositing fumes in the flue by means of a sufficient discharge of electricity, that is, the violent draught which is liable to exist there, and which would mechanically blow away any deposited dust. But Dr. Aitken suggests that regenerators might be used along with the electricity. The warm fumes might be taken to a cold depositor where, by the ordinary law of cold surfaces attracting warm dust particles, the impurities would be removed, and, when purified, the air would again be taken through a hot regenerator before being sent up the chimney. By a succession of these chambers, with the assistance of electrical currents, the air, impregnated with the most deleterious particles or valuable dust, would be rendered innocuous. The sewage of our towns must be cleared of its deleterious parts before being run into the streams which give drink to the lower animals, because an Act of Parliament enforces the process. Why, then, ought we not to have similar compulsion for making the smoke from chemical and other noxious works quite harmless before being thrown into the air, which contains the oxygen necessary for the life of human beings? There seems to be a good field before electricians to catch the smoke on the wing and deposit its dust on a large scale. This seems to be a matter beyond our reach at present, except in the scientist's laboratory, but certainly it is a consummation devoutly to be wished. End of chapter 25. Chapter 26 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patrick Wells. Meteorology by J.G. McPherson. Chapter 26. Radiation from Snow. One night, a most interesting paper by Dr. Aitken on radiation from snow was read by Professor Tate to the Fellows of the Royal Society of Edinburgh. I remember that Dr. Alex Buchan, the greatest meteorologist living, spoke afterwards in the very highest terms of the subject matter of the paper. This was corroborated by Lord Kelvin, Lord Maclaren, and Professor Crystal. Dr. Aitken had been testing the radiating powers of different substances. Snow in the shade on a bright day at noon is 7 degrees Fahrenheit colder than the air that floats upon it, whereas a black surface at the same is only 4 degrees cooler. This difference diminishes as the sun gets lower, and at night both radiate almost equally well. I select among the careful and numerous observations the notes on January 19th, 1886, for I took note of the cold of that day in my diary. It was the coldest day of the whole of that winter. the barometer was 28.8 inches, and the thermometer 4 degrees, that is, 28 degrees of frost. According to Dr. Buchan, that January had only 2 equal in average cold for 50 years. On January 19th at 10 a.m., when the air was at 20 degrees and the sky clear, a black surface registered 16 degrees and the upper layers of snow 12 degrees, showing a difference of 4 degrees when both surfaces were colder than the superincumbent air. It is curious to note that on February 5th of the same year, at the same hour when the sky was overcast, the air was at 23 degrees, the black surface registered 29 degrees, and the snow 25, showing again the difference of 4 degrees. But in this case, both surfaces were warmer than the air. In both cases, the radiation at night was equal. The small absorbing power of snow for heat reflected and radiated from the sky during the day must have a most important effect on the temperature of the air. The temperature of lands when covered with snow must be lower than when free from it, and when once a country has become covered with snow, there will be a tendency towards glacial conditions. But besides being a bad absorber of heat from the sky, snow is also a very poor conductor of heat. On that very cold night, January 18th, where there was a depth of 5.5 inches of snow on the ground and the night clear, with strong radiation, the temperature of the surface of the snow was 3 degrees Fahrenheit, and a minimum thermometer on the snow showed that it had been down to 0 some time before. A thermometer, plunged into the snow down to the grass, gave the most remarkable register of 32 degrees. Through the depth of 5.5 inches of snow, there was a difference of 29 degrees. This confirmed by removing the snow and finding that the grass was unfrozen. As the ground was frozen when the snow fell, it would appear that the earth's heat slowly thawed it under the protection of the snow. The protection afforded by the bad conducting power of snow is of great importance in the economy of nature. How vegetation could suffer were it exposed to a low temperature unprotected by the snow mantle, so that through the continued snow cools the air for animals that can look after their own heating. It keeps warm the soil, and vegetation prospers under the genial covering. The fine, rich look of the young wheat blades after a continued snow has melted must strike the most careless observer. Instead of the half-blackened tips and semi-sickly blades which we see in a field of young wheat after a considerable course of dry frost without snow, we have a rich, healthy green which shows the vital energy at work in the plants. Or even in the town gardens, after a continued snow has been melted away by a soft western breeze, we are struck with the white, peeping buds of the snowdrop and the finely springing grass in the sward. Yet the snow covering gives durability to cold weather. This has been demonstrated by Dr. Wyckoff, the distinguished Russian meteorologist. On this account, the spring months of Russia and Serbia are intensely cold. The plants, then, which in water are unable by locomotion to keep themselves in health, are protected by the snow mantle, which chills the air for animals that can keep themselves in heat by exercise. What a grand compensating power is here! End of chapter 26.
Chapter 27 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 27, Mountain Giants. Some mysterious physical phenomena can be clearly explained by the aid of science. The mountain giants that at times haunt the lonely valleys and strike with fear the superstitious dwellers there are only the enlarged shadows of living human beings cast upon a dense mist. The two most startling of these eerie phenomena are the specters of Adam's Peak and the Brocken. The phenomena sometimes to be observed at Adam's Peak and Ceylon are very remarkable. Many travelers have given vivid accounts of these. On one occasion, the Honorable Ralph Abercrombie, in his praiseworthy enthusiasm for meteorological research, went there with two scientific friends to witness the strange appearance. The conical peak, 1.5 miles high, overlooks a gorge west of it. When, then, the northeast monsoon blows the morning mist up the valley, light wreaths of condensed vapor pass to the right of the peak and catch the shadows at sunrise. This party reached the summit early one morning in February. The foreglow began to brighten the undersurface of the stratus cloud with orange, and patches of white mist filled the hollows. Soon the sun peeped through a chink in the clouds, and they saw the pointed shadow of the peak lying on the misty land. Then a prismatic circle with the red inside formed round the shadow. The meteorologist waved his arms about, and immediately he found giant shadowy arms moving in the center of the rainbow. Soon they saw a brighter and sharper shadow of the peak, encircled by a double bow, and their own spectral arms more clearly visible. The shadow, the double bow, and the giant forms combined to make this phenomenon the most marked in the whole world. The question has been frequently asked, why are such aerial effects not more widely observed? There are not many mountains of this height and of a conical shape, and still fewer can there be where a steady wind, for months together, blows up a valley so as to project the rising morning mist at a suitable height and distance on the western side, to catch the shadow of the peak at sunrise. The most famous place in Europe for witnessing the awe-inspiring phenomenon is the Brocken in Germany, 3,740 feet in height. The only great disappointment there is that the conditions rarely combine at sunrise or sunset to have the spectre successful. In July 1892, my daughter and I were spending some weeks at Hardsburg, and of course we had to visit the Brocken and take stock of the world-known phenomenon. At midday, the air at that flat summit was cold, clear, and hard. The boulders are of enormous size, and near the Noah's Ark Hotel and Observatory many are piled up in a mass, on which the observers stand at the appointed time for having their shadows projected on the misty air in the valleys. At 5 o'clock in the afternoon the sky was brilliantly clear on the summit of the Brocken, but the wind was rising from the sun's direction, and the mist was filling up the widespread eastern valley. We stood on the spectre boulders, and our shadows were thrown on the grass just as at home. However, they fell upon large patches of white heather, which there is very plentiful. At 6 o'clock the sun was still shining beautifully, and we anxiously waited for the time when it would be low enough to raise our shadows to the misty wall. An hour afterwards 100 visitors were out, and many of us were on the spectre stones. There was great excitement and anticipation of the weird appearances which had attracted us from such a distance. But, almost at the moment of success, the sun descended behind a belt of purple cloud, and all we saw was part of a rainbow on the misty hollow, for the sun never appeared again. This was intensely saddening, seeing that but for that stratum of cloud above the horizon, the phenomenon would have been graphically displayed. The cold became suddenly intense, and we had to sleep with a freezing mist enveloping the hotel. In vain did we wait for the wakening call to tell us of sunrise, for the sun could not pierce the mist, and we had to return home disappointed. Sometimes the rainbow colors assume the shapes of crosses instead of circles. Occasionally a bright halo will be seen above the shadow head of the observer, concentric rainbows enclosing all. In some recorded cases the grand effect must have been simply glorious. Scientific observation has done much to dispel the superstition which has clung so tenaciously to the Highland mind. The lonely grandeur of the weird mountain giants has been clearly explained as perfectly natural, yet the awe-striking feeling cannot be entirely driven off. End of Chapter 27. Mountain Giants. Recording by Pamela Krantz.
Chapter 28 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J. G. McPherson. Chapter 28. The Wind. Once was the remark pointedly made, "The wind bloweth where it listeth," and that is nearly true still. The leading winds are under the calculation of the meteorologist, but the others will not be bound by laws. Yet there are instruments for measuring the velocity and force of the wind after it is on, but whence it comes is a different matter. A gentle air moves at the rate of 7 miles an hour, a hurricane from 80 to 150 miles, pressing with 50 pounds on the square foot, exposed to its fury. Some of the gusts of the Tay Bridge storm in 1879 had a velocity of 150 miles an hour, with a pressure of 80 to 90 pounds to the square foot. Before steamers supplanted so many sailing vessels, seamen required to be always on the alert as to the direction and strength of the wind and the likelihood of any sudden change, and they chronicled 12 different strengths, from faint air to a storm. In general, the wind may be considered to be the result of a change of pressure and temperature in the atmosphere at the same level. The air of a warmer region, being lighter, ascends and gives place to a current of wind from a colder region. These two currents, the higher and the lower, will continue to blow until there is equilibrium. The trade winds are regular and constant. These were much followed in the days of old. A vast amount of air in the tropics gets heated and ascends, being lighter, and travels to the colder north. A strong current rushes in from the north to take its place, but the earth rotates round its axis from west to east, and the combined motions make two slant wind directions, which are called the trade winds, because they were so important in trade navigation. Among the periodical winds are the land and sea breezes. During the day, the land on the sea coast is warmer than the sea. Accordingly, the air over the land becomes heated and ascends, the fine cool breeze from the sea taking its place. Towards evening there is the equilibrium of temperature, which produces a temporary calm. Soon the earth chills, and the sea is counterbalancingly warm. As sea water is steadier as to temperature than is land, the air over the sea becomes warmer and ascends, the current from the land rushing in to take its place. Hence, during the night the wind is reversed, until in the morning again the equilibrium is restored, and there is a calm, so far as these are concerned. These are therefore called the land and sea breezes. Of course, it is within the tropics that these breezes are most marked. By the assistance of other winds, a hurricane will there occasionally destroy towns and bring about much damage and loss of life. But better that hundreds should perish by a hurricane than thousands by the pestilence which, but for the storm, would have done its dire work. In countries where the differences of pressure are more marked than the differences of temperature, in the surrounding regions the strength of the wind thereby occasioned is far stronger than the land and sea breezes. The variable winds are more conflicting. These depend on purely local causes for a time, such as the nature of the ground covered with vegetation or bare, the physical configuration of the surface, level or mountainous, the vicinity of the sea or lakes, and the passage of storms. Among these winds are the Simoon and Sirocco. The east winds, which one does not care about in the British Isles during the springtime, are occasioned by the powerful northern current which rushes south from the northern regions in Europe. Dr. Buchan points out a very common mistake among even intelligent observers who shudder at the hard east winds. It is generally held that these winds are damp. They are unhealthy, but they are dry. It is quite true that many easterly winds are peculiarly moist. All that precedes storms are so far damp and rainy, and it is owing to the circumstance that on the east coast of Scotland the east winds are searching and carry most of the annual rainfall there. But all of these moist easterly winds, however, soon turn to some westerly point. The real east wind, so much feared by invalids, does not turn to the west. It is exceeding dry. Curious is it that brain diseases, as well as consumption, reach their height in Britain while east winds prevail. Once in Edinburgh, during the early spring, I had rheumatic fever, and during my convalescence my medical adviser, Dr. Menzies, would not let me have a short drive until the wind changed to the west. The first thing I anxiously watched in the morning was the flag on the castle, and for nearly 2 months it always waved from the east. How heart-depressing! Creatures are we in the hands of nature's messengers. We so much depend upon the weather for our happiness. Joyful are we when the honey-laden zephyr waves the long grass in June, or when the gentle wind, a sweet and passionate wooer, kisses the blushing leaf. Compared with this, how terrible is Shakespeare's allusion to the appalling aspects of the storm. I have seen tempests when the scolding winds have rived the knotty oaks, and I have seen the ambitious ocean swell and rage in foam, to be exalted with the threatening clouds. But never till tonight, never till now, did I go through a tempest, dropping fire. End of chapter 28. Chapter 29 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Meteorology by J.G. McPherson. Chapter 28. Cyclones and Anti-Cyclones. The criticism of the weather in the meteorological column of our daily newspapers invariably speaks of cyclones. It is therefore advisable to give as plain an explanation of these as possible. Cyclones are storm winds. Their nature has to be carefully studied by meteorologists who are industriously at work to ascertain some scientific basis for the atmospheric movements. What is the cause of the spiral movement in storm winds? In their center, the depression of the barometer is lowest because the atmosphere there is lightest. As the walls of the spiral are approached, the barometer rises. Dr. Aitken has ingeniously hit upon an experiment to illustrate a spiral in air. All that is necessary is a good fire, a free-going chimney, and a wet cloth. The cloth is hung up in front of the fire and pretty near it, so that steam rises steadily from its surface, and when there are no air currents in the room, the steam will rise vertically, keeping close to the cloth. But if the room has a window in the wall, at right angles to the fireplace, so as to cause the air coming from it to make a cross-current past the fire, then a cyclone will be formed, and the vapor from the cloth will be seen circling round. When the cyclone is well formed, all the vapor is collected into the center of the cyclone, and forms a white pillar extending from the cloth to the chimney. This experiment shows that no cyclone can form without some tangential motion in the air entering the area of low pressure. Now, to illustrate the spiral approach, fill with water a cylindrical glass vessel, say 15 inches in diameter and 6 inches deep. Have an orifice with a plug a little from the center of the bottom. Remove the plug. The water runs out, passing round the vessel in a vortex form. But as the passage between the orifice, or center of the cyclone, and the temporary division is narrower than in any other place, the water has to pass this part much more quickly than at any other place, and this curious result is observed. The top of the cyclone no longer remains over the orifice, but travels in the direction of the water, which is moving most speedily. Similar to this is the cyclone in the atmosphere. Its center also moves in the direction of the quickest flowing wind that enters it. Dr. Aitken is of opinion that, in forecasting storms, too little attention has been paid to the anti-cyclones. They do more than simply follow and fill up the depression made by the cyclones. They initiate and keep up their own circulation, and collect the materials with which the cyclones produce their effect. Neither could work efficiently without the other. Suppose a large area of the earth over which the air is still in bright sunshine. After a time, when the air gets heated and charged with vapor, columns of air would begin to ascend in a disorderly fashion. But suppose an anticyclone is blowing at one side of this area. When the upper air descends to the earth, it spreads outwards in all directions, but the earth's rotation interferes and changes the radial into a spiral motion. The anticyclonic winds will prevent the formation of local cyclones and drive all the moist, hot air to its circumference, just above the earth. The anticyclone forces its air tangentially into the cyclone and gives it its direction and velocity of rotation, also the direction and rate of travel of the center of depression. The Earth's rotation is the original source of the rotatory movements, but both intensify the initial motion. Accordingly, the cyclone must travel in the direction of the strongest winds blowing into it, just as the vortex in the vessel with the eccentric orifice traveled in the direction of the quickest moving water. This is verified by a study of the synoptic charts of the Meteorological Office. The sun's heat has always been looked upon as the main source of the energy of our winds, but some account must also be taken of the effects of cold. It is well known that the mean pressure over continental areas is high during winter and low during summer. As the sun's rays during summer give rise to the cyclonic conditions, so the cooling of the earth during winter gives rise to the anticyclonic conditions. It is found during the winter months in several parts of the continent that as the temperature falls, the pressure rises, producing anticyclones over the cold area, whereas when the temperature begins to rise, the pressure falls and cyclones are attracted to the warming area. Small natural cyclones are often seen on dusty roads, the whirling column having a core of dusty air and the center of the vortex traveling along the road, tossing up the dust in a very disagreeable way to pedestrians. Sometimes such a cyclone will toss up dry leaves to a height of 4 or 5 feet. They are very common, but it is only when dust, leaves, or other light material is present that they are visible to the eye. End of chapter 29.
Chapter 30 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patty Cunningham. Meteorology by J.G. McPherson. Chapter 30, Rain Phenomena. The soft rain on a genial evening, or the heavy thunder showers on a broiling day, are too well known to be written about. Sometimes rain is earnestly wished for, and at other times it is dreaded according to the season, seed time, or harvest. Some years, like 1826, are very deficient in rainfall, when the corn is stunted and everything is being burnt up. Other years, like 1903, there is an oversupply, causing great damage to agriculture. The year 1903 will long be remembered for its continuous rainfall. It is the record year. No year comes near it for the total rainfall all over the kingdom. Rain is caused by anything that lowers the temperature of the air below the dew point, but especially by winds. When a wind has blown over a considerable area of ocean onto the land, there is a likelihood of rain. When this wind is carried on to higher latitudes or colder parts, there is a certainty of rain. Of course, in the latter case, the rain will fall heavier on the wind side than on the lee side. For short periods, the heaviest falls, or plouts of rain, are during thunderstorms. When the raindrops fall through a broad, cold stratum of air, they are frozen into hail, the particles of which sometimes reach a large size, like stones. Of course, waterspouts now and again are of terrible violence. One of the heaviest rainfalls yet recorded in Great Britain was about 2¼ inches in 40 minutes at Lednathie, Hertfordshire, in 1887. Now 1 inch deep of rain means 100 tons on an imperial acre, so the amount of water falling on a field during that short time is simply startling. The heaviest fall for one day was at Ben Nevis Observatory, being fully 7¼ inches in 1890. In other parts of the world, this is far exceeded. In one day at Brownsville, Texas, nearly 13 inches fell in 1886. On the Khasi Hills, India, 30 inches on each of 5 successive days were registered. At Gibraltar, 33 inches were recorded in 26 hours. The heaviest rainfalls of the globe are occasioned by the winds that have swept over the most extensive ocean areas in the tropics. On the summer winds, the rainfall of India mainly depends. When this fails, there is most distressing drought. Reservoirs are being erected to meet emergencies. From Dr. Buchanan's statistics, it is found that the annual rainfall at Mahabaleshwar is 263 inches, at Sandaway 214, and at Cherrapunji 472 inches, the largest known rainfall anywhere on the globe. Over a large part of the Highlands of Scotland, more than 80 inches fall annually, while in some of the best agricultural districts there, it does not exceed 30 inches. Of all meteorological phenomena, rainfall is the most variable and uncertain. Simons gives us tentative results from 20 years' observations in London. 1. In winter, the nights are wetter than the days. 2. In spring and autumn, there is not much difference. 3. In summer, nearly half as much again by day as by night. The wearisomeness of statistics may be here relieved by a short consideration of the splash of a drop of rain. Watching the drop splashes on a rainy day in the outskirts of the city, when unable to get out, I brought to my recollection the marvelous series of experiments made by Professor A.M. Worthington in connection with these phenomena. Of course, I could not see to proper advantage the formation of the splashes, as the heavy raindrops fell into these tiny lakes on the quiet road. There is not the effect of the huge thunder drops in a stream or pool. The building up of the bubbles here is not perfect, for the domes fail to close, nor are the emergent columns visible to the naked eye. It is a pity, for R.L. Stevenson once wrote of them in his delightful inland voyage, when he canoed in the Belgian canals, as thrown up by the rain into an infinity of little crystal fountains. Beautiful is this effect if one is under shelter, every dome seeming quite different in contour and individuality from all the rest. But terrible is it when out fishing on Loch Earn, even with the good-humored old admiral, when the heavy thunder drops splash up the crystal water, and one gets soaked to the skin, sportsmanlike, despising an umbrella. There is, however, a scientific interest about the splash of a drop. The phenomenon can be best seen indoors by letting a drop of ink fall upon the surface of pure water in a tumbler, which stands on white paper. It is an exquisitely regulated phenomenon, which very ideally illustrates some of the fundamental properties of fluids. When a drop of milk is let fall upon water colored with aniline dye, the center column of the splash is nearly cylindrical, and breaks up into drops before or during its subsequent descent into the liquid. As it disappears below the surface, the outward and downward flow causes a hollow to be again formed, up the sides of which a ring of milk is carried, while the remainder descends to be torn a second time into a beautiful vortex ring. This shell or dome is a characteristic of all splashes made by large drops falling from a considerable height, and is extremely pretty. Sometimes the dome closes permanently over the imprisoned air and forms a large bubble floating upon the water. The most successful experiments, however, had been carried through by means of instantaneous photography, with the aid of a Leyden jar spark, whose duration was less than the 10,000,000th of a second. But the simple experiments, without the use of the apparatus, will while away a few hours on a rainy afternoon, when condemned to the penance of keeping within doors. End of Chapter 30. Recording by Patty Cunningham.
Chapter 31 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 31. The Meteorology of Ben Nevis. Several large and very important volumes of the Royal Society of Edinburgh are devoted to statistics connected with the meteorology of Ben Nevis. Most of the abstracts have been arranged by Dr. Buchan, while Messrs. Buchanan, Omand, and Rankin have taken a fair share of the work. This observatory, as Mr. Buchanan remarks, is unique, for it is established in the clouds, and the observations made in it furnish a record of the meteorology of the clouds. It is 4,406 feet above the level of the sea, and as there is a corresponding observatory at Fort William, at the base of the mountain, it is peculiarly well fitted for important observations and weather forecasting. The mountain, too, is on the west sea coast of Scotland, exposed immediately to the winds from the Atlantic, catching them at first hand. It is lamentable to think that when the importance of the observations made at the two observatories was becoming world known, funds could not be got to carry them on. Ben Nevis is the highest mountain in the British Islands, best fitted for meteorological observations, yet these have been stopped for want of money. Dr. Buchan's valuable papers were published before anyone dreamed of the stoppage of the work, which had such an important bearing on men engaged in business or taken up with open-air sport. From these I shall sift out a few facts that even mute, inglorious meteorologists may be interested in knowing. For a considerable time, the importance of the study of the changes of the weather has come gradually to be recognized, and an additional impetus was given to the prosecution of this branch of meteorology when it was seen that the subject had intimate relations to the practical question of weather forecasts, including storm warnings. Weather maps showing the state of the weather over an extensive part of the surface of the globe began to be constructed, but these were only indicators from places at the level of the sea. The singular advantages of a high-level observatory occurred to Mr. Milne Home in 1877, and Ben Nevis was considered to be in every respect the most suitable in this country. The Meteorological Council of the Royal Society of London offered in 1880 unsolicited £100 annually to the Scottish Meteorological Society to aid in the support of an observatory, the only stipulation being that the Council be supplied with copies of the observations. From June to October in 1881, Mr. Wragg made daily observations at the top of the Ben, and simultaneous observations were made by Mrs. Wragg at Fort William. A second series on a much more extended scale was made in the following summer. Funds were secured to build an observatory, and in November 1883 the regular work commenced, consisting of hourly observations by night as well as by day. Until a short time ago these were carried on uninterruptedly. Telegraphic communications of each day's observations were sent to the morning newspapers, and now we are disappointed at not seeing them for comparison. The whole of the observations of temperature and humidity were of necessity eye observations, for self-registering thermometers were comparatively useless when the wind was sometimes blowing at the rate of 100 miles an hour. Saturation was so complete in the atmosphere that everything exposed to it was dripping wet. Every object exposed to the outside frosts of winter soon became thickly encrusted with ice. Snowdrifts blocked up exposed instruments. Accordingly, the observers had to use their own eyes, often at great risks. The instruments in the Ben Nevis Observatory and in the observing station at Fort William were of the best description. Both stations were in positions where the effects of solar and terrestrial radiation were minimized. No other pair of meteorological stations anywhere in the world are so favorably situated as these two stations for supplying the necessary observations for investigating the vertical changes of the atmosphere. It is to be earnestly hoped, therefore, that funds will be secured to resume the valuable work. The rate of the decrease of temperature with height there is 1 degree Fahrenheit for every 275 feet of ascent on the mean of the year. The rate is most rapid in April and May, when it is 1 degree for each 247 feet, and least rapid in November and December, when it is 1 degree for 307 feet. This rate agrees closely with the results of the most carefully conducted balloon ascents. The departures from the normal differences of temperature, but more especially the inversions of temperature and the extraordinarily rapid rates of diminution with height, are intimately connected with the cyclones and anti-cyclones of northwestern Europe, and form data as valuable as they are unique in forecasting storms. The most striking feature of the climate of Ben Nevis is the repeated occurrence of excessive droughts. For instance, in the summer and early autumn of 1885, low humidities and dew points frequently occurred. Corresponding notes were observed at sea level. During nights when temperature falls through the effects of terrestrial radiation, those parts of the country suffer most from frosts over which very dry states of the air pass or rest, whereas those districts over which a more humid atmosphere hangs will escape. On the night of August 31st of that year, the potato crop on Speyside was totally destroyed by the frost, whereas at Dalnaspidal, in the district immediately adjoining, potatoes were scarcely, if at all, blackened. The mean annual pressure at Ben Nevis was 25.3 inches, and at Fort William 29.8, the difference being 4.5 inches for the 4,400 feet. For the whole year, the difference between the mean coldest hour, 5 a.m., and the warmest hour, 2 p.m., is 2 degrees. For the 5 months, from October to February, the mean daily range of temperature varied only from 0.6 to 1.5. This is the time of the year when storms are most frequent, and this small range in the diurnal march of the temperature is an important feature in the climatology of Ben Nevis, for it presents, in nearly their simple form, the great changes of temperature accompanying storms and other weather changes, which it is so essential to know in forecasting weather. The daily maximum velocity of the wind occurs during the night, the daily differences being greatest in summer and least in winter. A blazing sun in the summer daily pours its rays on the atmosphere, and a thick envelope of cloud is apparently but little influence on the effect of the sun's rays. Thunderstorms are essentially autumn and winter phenomena, being rare in summer. According to Mr. Buchanan, the weather on Ben Nevis is characterized by great prevalence of fog or mist. In continuously clear weather, it practically never rains on the mountain at all. In continuously foggy weather, on the other hand, the average daily rainfall is 1 inch. There is a large and continuous excess of pressure in clear weather over that of foggy weather. The mean temperature of the year is 3.5 degrees higher in clear than in foggy weather. In June, the excess is 10 degrees. The nocturnal heating in the winter is very clearly observed. This has been noticed before in balloons as well as on mountains. The fog and mist in winter are much denser than in summer. Whether wet or dry, the fog which characterizes the climate of the mountain is nothing but cloud under another name. End of section 31. The Meteorology of Ben Nevis. Recording by Pamela Krantz. Chapter 32 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Krantz. Meteorology by J.G. McPherson. Chapter 32, The Weather and Influenza. Some remarkable facts have been deduced by the late Dr. L. Gillespie, Medical Registrar, from the records of the Royal Infirmary of Edinburgh. He considered that it might lead to interesting results if the admissions into the medical wards were contrasted with the varying states of the atmosphere. The repeated attacks of influenza made him pay particular attention to the influence of the weather on that disease. The meteorological facts taken comprise the weekly type of weather, in other words, cyclonic or anticyclonic, the extremes of temperature for the district for each week, and the mean weekly rainfall for the same district. More use is made of the extremes than of the mean, for rapid changes of temperature have a greater influence on disease than the actual mean. The period which he took up comprises the 7 years 1888 through 1895. There was a yearly average of admissions of 3,938, so that he had a good field for observation. 6 distinct epidemics of influenza, varying in intensity, occurred during that period, yet there had been only 23 attacks between 1510 and 1890. Accordingly, these 6 epidemics must have had a great influence on the incidence of disease in the same period, knowing the vigorous action of the poison on the respiratory, the circulatory, and the nervous systems. The epidemics of influenza recorded in this country have usually occurred during the winter months. The first epidemic, which began on the 15th of December, 1889, and continued for 9 weeks, was preceded by 6 weeks of cyclonic weather, which was not, however, accompanied by a heavy rainfall. Throughout the course of the disease, the type continued to be almost exclusively cyclonic, with a heavy rainfall, a high temperature, and a great deficiency of sunshine. The 4 weeks immediately following were also chiefly cyclonic, but with a smaller rainfall. The summer epidemic of 1891 followed a fine winter and spring, during which anticyclonic conditions were largely prevalent. But the epidemic was immediately preceded by wet weather and a low barometer. It took place in dry weather and was followed by wet cyclonic weather in turn. The great winter epidemic of 1891 followed an extremely wet and broken autumn. Simultaneously with the establishment of an anticyclone with east wind, practically no rain, and a lowering temperature, the influenza commenced. Great extremes in the temperature followed, the advent of warmer weather and more equable days witnessing the disappearance of the disease. The fourth epidemic was preceded by a wet period, ushered in by dry weather, accompanied by great heat, and its close occurred in slightly wetter weather, but under anticyclonic conditions. The fifth outbreak began after a short anticyclone had become established over our islands, continued during a long spell of cyclonic weather with a considerable rainfall, but was drowned out by heavy rains. The last appearance of the modern plague, of which Dr. Gillespie's paper treats, commenced after cold and wet weather, continued in very cold but drier weather, and subsided in warmth with a moderate rainfall. The conditions of these 6 epidemics were very variable in some respects, and regular in others. The most constant condition was the decreased rainfall at the time, when the disease was becoming epidemic. Anticyclonic weather prevailed at the time. According to Dr. Gillespie, the tables seem to suggest that a type of weather, which is liable to cause catarrhs and other affections of the respiratory tract, precedes the attacks of influenza, but that the occurrence of influenza in epidemic form does not appear to take place until another and drier type has been established. As the weather changes, the affected patients increase with a rush. He is of opinion that the supposed rapid spread of influenza on the establishment of anticyclonic conditions may be explained in this way. The air in the cyclonic vortex, drawn chiefly from the atmosphere over the ocean, is moist, and contains none of the contagion. The air of the anticyclone, derived from the higher strata, and thus from distant cyclones, descending, blows gently over the land to the nearest cyclone, and, being drier, is more able to carry suspended particles with it. He considers that temperature has nothing to do with the problem, except in so far as the different types of weather may modify it. The infirmary records point to the occurrence of similar phenomena recorded on previous occasions. Accordingly, if such meteorological conditions are not indispensable to the spread of influenza in epidemic form, they at least afford favorable facilities for it. End of Chapter 32. The Weather and Influenza. Recording by Pamela Krantz.
Chapter 33 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2012. Meteorology by J.G. McPherson. Chapter 33. Climate. One is not far up in years, in Scotland at any rate, without practically realizing what climate means. He may not be able to put it in words, but easterly haws, chilling rime, drizzling mists, dagging fogs, and soddening rains speak eloquently to him of the meaning of climate. Climate is an expression for the conditions of a district with regard to temperature and its influence on the health of animals and plants. The sun is the great source of heat, and when its rays are nearly perpendicular, as at the tropics, the heat is greater on the earth than when the slanted rays are gradually cooled in their passage. As one passes to a higher level, he feels the air colder until he reaches the fluctuating snow line that marks perpetual snow. The temperature of the atmosphere also depends upon the radiation from the earth. Heat is quite differently radiated from a long stretch of sand, a dense forest, and a wide breadth of water. Strange is it that a newly ploughed field absorbs and radiates more heat than an open lea. The equable temperature of the seawater has an influence on coast towns. The Gulf Stream from the Gulf of Mexico heats the ocean on to the west coast of Britain and mellows the climate there. The rainfall of a district has a telling effect on the climate. Boggy land produces a deleterious climate, if not malaria. Over the world, generally, the prevailing winds are grand regulators of the climate in the distinctive districts. A wooded valley, like the greatest in Britain, Strathmore, has a health-invigorating power. What a calamity it is, then, that so many extensive woods, destroyed by the awful hurricane 12 years ago, are not replanted. Some people can stand with impunity any climate. Their leather lungs cannot be touched by extremes of temperature, but ordinary mortals are mere puppets in the hands of the goddess climate. Hence, health resorts are munificently got up and splendidly patronized by people of means. The poor, fortunately, have been successful in the struggle for existence by innate hardiness. Otherwise, they would have had a bad chance without ready cash for purchasing health. It may look ludicrous at first sight, but it seems none the less true that the variation of the spots on the sun has something to do with climate, even to the produce of the fields. On close examination, with a proper instrument, the disk of the sun is found to be here and there studded with dark spots. These vary in size and position day after day. They always make their first appearance on the same side of the sun. They travel across it in about 14 days, and they disappear on the other side. There is a great difference in the number of spots visible from time to time. Indeed, there is what is called the minimum period, when none are seen for weeks together, and a maximum period, when more are seen than at any other time. The interval between two maximum periods of sunspots is about 11 years. This is a very important fact which has wonderful coincidences in the varied economy of nature. Kirchhoff has shown, by means of the spectroscope, that the temperature of a sunspot must be lower than that of the remainder of the solar surface. As we must get less heat from the sun when it is covered with spots than when there are none, it may be considered a variable star with a period of 11 years. Balfour Stewart and Lockyer have shown that this period is in some way connected with the action of the planets on the photosphere. As we have already mentioned, the variations of the magnetic needle have a period of the same length, its greatest variations occurring when there are most sunspots. Aurorae and the currents of electricity which traverse the Earth's surface follow the same law. This remarkable coincidence set men a-thinking. Can the varying condition of the sun exert any influences upon terrestrial affairs? Is it connected with the variation of rainfall, the temperature and pressure of the atmosphere, and the frequency of storms? Has the regular periodicity of 11 years in the sunspots no effect upon climate and agricultural produce? Mr. F. Chambers of Bombay has taken great trouble to strike, as far as possible, a connection between the recurring 11 years of sunspots and the variation of grain prices. He arranged the years from 1783 to 1882 in 9 groups of 11 years, and, from an examination of his tables, we find that there is a decided tendency for high prices to recur at more or less regular intervals of about 11 years, and a similar tendency for low prices. An occasional slight difference can be accounted for by some abnormal cause, as war or famine. Amid all the apparently irregular fluctuations of the yearly prices, there is in every one of the 10 provinces of India a periodical rise and fall of prices once every 11 years, corresponding to the regular variation which takes place in the number of sunspots during the same period. If it were possible to obtain statistics to show the actual outturn of the crops each year, the 11 yearly variations calculated therefrom might reasonably correspond with the sunspot variations even more closely than do the price variations. This is a remarkable coincidence, if nothing more. What if it were yet possible to predict the variations of prices in the coming sunspot cycle? Such a power would be of immense service. By its aid it could be predicted that, as the present period of low prices has followed the last maximum of sunspots, which was in the year 1904, it will not last much longer, but that prices must gradually keep rising for the next 5 years. Could science really predict this, it would be studied by many and blessed by more. Yet the strange coincidence of a century's observations renders the conclusions not only possible, but to some extent probable. End of chapter 33.
Chapter 34 of Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Patty Cunningham. Meteorology by J.G. McPherson. Chapter 34. The Challenger Weather Reports. The Challenger expedition, commenced by Sir Wyville Thomson, and after his death continued by Sir John Murray, with an able staff of assistants for the several departments, was one of the splendid exceptions to the ordinary British government stinginess in the furtherance of science. The results of the expedition were printed in a great number of very handsome volumes at the expense of the government. And the valuable deductions from the Challenger's weather reports by Dr. Alex Buchan in his atmospheric circulation have thrown considerable light upon oceanic weather phenomena. For some of his matured opinions on these, I am here much indebted to him. Humboldt in 1817 published a treatise on isothermal lines, which initiated a fresh line for the study of atmospheric phenomena. An isotherm is an imaginary line on the Earth's surface passing through places having a corresponding temperature either throughout the year or at any particular period. An isobar is an imaginary line on the Earth's surface connecting places at which the mean height of the barometer at sea level is the same. To isobars as well as to isotherms, Dr. Buchan has devoted considerable attention. In 1868, he published an important series of charts containing these, with arrows for prevailing winds over the Earth for the months of the year. In this way, what are called synoptic charts were established. In the Challenger report are shown the various movements of the atmosphere, with their corresponding causes. It is thus observed that the prevailing winds are produced by the inequality of the mass of air at different places. The air flows from a region of higher to a region of lower pressure, i.e., from where there is an excessive mass of air to fill up some deficiency. And this is the great principle on which the science of meteorology rests, not only as to winds, but as to weather changes. Of the sun's rays which reach the earth, those that fall on the land are absorbed by the surface layer of about 4 feet in thickness, but those that fall on the surface of the ocean penetrate, as shown by the observations of the Challenger expedition, to a depth of about 500 feet. Hence, in deep waters, the temperature of the surface is only partially heated by the direct rays of the sun. In mid-ocean, the temperature of the surface scarcely differs 1 degree Fahrenheit during the whole day, while the daily variation of the surface layer of land is sometimes 50 degrees. The temperature of the air over the ocean is about 3 times greater than that of the surface of the open sea over which it lies, but near land this increases to 5 times. The elastic force of vapor is seen in its simplest form on the open sea, as disclosed by these reports. It is lowest at 4 a.m. and highest at 2 p.m. The relative humidity is just the reverse. When the temperature is highest, the saturation of the air is lowest, and vice versa. So on land, when the air, by radiation of heat from the earth, is cooled below the dew point, dew is produced, and, at the freezing point, hoar-frost. The Challenger reports, too, show that the force of the winds on the open sea is subject to no distinct and uniform daily variation, but that on nearing land, the force of the wind gives a curve as distinctly marked as the ordinary curve of temperature. That force is lowest from 2 to 4 a.m. and highest from 2 to 4 p.m. Each of the 5 great oceans gives the same result. At Ben Nevis, on the other hand, these forces are just reversed in strength. It is also shown by the Challenger observations that on the open sea the greatest number of thunderstorms occur from 10 p.m. to 8 a.m., and from this, Dr. Buchan concludes that over the ocean, terrestrial radiation is more powerful than solar radiation in causing those vertical disturbances in the equilibrium of the atmosphere which give rise to the thunderstorm. End of Chapter 34. Recording by Patty Cunningham.
Chapter 35, Meteorology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Gonzalez. Meteorology by J.G. McPherson. Chapter 35. Weather Forecasting. To foretell with any degree of certainty the state of the weather for 24 hours is of immense advantage to businessmen, tourists, fishermen, and many others. The weather is everybody's business, and the probabilities of accurate forecasts are so improving that all are more or less giving attention to the morning meteorological reports. Weather forecasting depends on the principle from vast experience that, if an event happens,
a second is likely to follow, according to the extent and accuracy of the data, will be the strength of the probability of correct forecast, and the great end of popular meteorology is to demonstrate this. We have given some explanations of the weather in some respects unique, and a careful consideration of these explanations will the more convince the reader of the importance of the subject. No doubt the changes of the weather are extremely complex, at times baffling, and the wonder is that forecasts come so near to the truth. For instance, the year 1903 almost defied the ordinary rules of weather, for it broke the record for rainfall, and last year, so repulsive and unseasonable was the spring, and that there seemed to be a virtual withdrawal of the season, as the recession of spring. Speak about borrowing days. We had equinoctial gales of March about middle of April. On very few days we had a clear shining to cheer us after rain, but a bitter cold dried up any genial moisture. An old farmer remarked that we're going over far north. No one could account for the backwardness of the season, unless with the cheering songs to the grove charmers, one would have forgotten the time of the year. In March of this year, at Swarthmore, the barometer fell from 3.5 inches, the highest of the year, to 26.5 in 5 days without unfavourable weather following. Then it again rose to 30.5, then fell to 28.45. Followed by a rise to 28.7 without any peculiar change. But in 2 days it fell to 28.4, the lowest for years, followed by a deluge of rain and a perfect hurricane for several hours. While the temperature was fortunately mild, it was only evident at the end that this universal storm had been brewing some days before. All are familiar with the ordinary prognostics of good and bad weather. A broad round the moon, in her troubled heaven, indicates a storm of rain or wind. With the dark crimson sun in the evening throws the brilliant bronze light in the gables and dead leaves, we are sure that there is an intense radiation from earth to form dew, or even hoar-frost. According to the meteorological folklore, the weather of the summer season is indicated by the foliation of the oak and ash trees. If the oak comes first into leaf, the summer will be hot and dry. If the ash has the precedence, it will be wet and cold. Looking over the observations of the budding of these two trees for half a century, I find that the weather law adage has been pretty correct. The ash was up before the oak a full month in the years 1816, 17, 21, 23, 28, 29, 30, 38, 40, 45, 50, and 59, and the summer and the autumn of this year are unfavourable. Again, the oak was out before the ash several weeks in the years 1818, 19, 20, 22, 24, 25, 26, 27, 33, 34, 35, 36, 37, 42, 46, 54, 68, and 69. The summers during this year were dry and warm, and the harvests abundant. One can never think of this weather prognostic from nature without recalling the soul song of Tennyson's Princess. While lingering she to clothe her heart with love, delaying as the tender ash delays to clothe herself when all the woods are green. On a muggy morning, a sudden clearness in the south downs the ploughman, and yet enough blue in the sky. That make a pair of bricks, cheers one with the assurance of coming dry and sunny weather. The low flying of the swallows betokens rain, as well as any unseasonable dancing of midges in the evening. Sore cones on the feet and rheumatism in the joints are direful precursors. The leaves are all a-tremble before the approach of thunder. But throughout this volume I have given many illustrations. But one of the largest and most important practical problems of meteorology is to ascertain the cause which storms follow, and the causes by which that cause is determined, so that a forecast may thereby be made, not only of the certain approach of a storm, but the particular direction and force of the storm. The method of conducting this large inquiry most effectively was devised by the French astronomer Leverrier, the great aspirant, with our own coach Adams, for the discovery of planet Neptune. He began to carry this out in 1858, by the daily publication of weather data, followed by a synchronous weather map, which showed graphically for the morning of the day of publication the atmospheric pressure and the direction and force of the wind, together with tables of temperature, rainfall, cloud and sea disturbances from a large number of places in all parts of Europe. It is from similar maps that forecasts of storm are still framed and suitable warnings issued, and a mass of information is being collected by telegraph from 60 stations in the British Islands, and company of the state of the weather at 8 o'clock every morning, and analysed and arranged at the Meteorological Office in London for the evening's forecast over different districts of the country. A juster knowledge is being now acquired of those great atmospheric movements and other changes which form the groundwork of weather forecasting. The Meteorological Office, Westminster, entirely distinct from the Royal Meteorological Society, is administered by Council, Chairman Sir R. Strachey, Scottish member Dr. Buchan, selected by the Royal Society. It employs a staff of over 40. The chief departments relate to 1. Ocean meteorology, including the collection, tabulation, and discussion of meteorological data from British ships, the preparation of ocean weather charts, and the issue of meteorological instruments to the Royal Navy and Mercantile Marine. 2. Weather telegraphy, including the reception of telegrams twice a day from selected stations for the preparation of the daily reports and weather forecasts. Representatives of newspapers and company receive copies of the 11 a.m. forecast based on the 8 a.m. observations, and also of the 8:30 p.m. forecast based on the observations received earlier in the day. In summer and autumn harvest forecasts are issued by telegraph to individuals who will defray the cost. The office also collects climatological data from a number of voluntary and some subsidized stations. The first order stations include Valencia, Falmouth, Kew and Aberdeen. These are self-recording instruments of high precision, giving a continuous record of the meteorological elements. A government commission which sat last year, under the retired Honourable Sir Herbert Maxwell, have issued a report recommending a number of changes in the management and constitution of the Meteorological Office, and considerable modifications are unlikely to take place in the near future. In his evidence before that commission, the chairman of the council acknowledged that the great function of meteorologists is the collection of facts, but the interpretation of those collected facts in a scientific manner is still in a very immature condition. Dr. Buchan, in his evidence, confessed that forecasting by the council is purely by rule of thumb. It is not possible to lay down hard and fast rules for forecasting. With regard to the storm warning telegrams, as a rule, the earliest trustworthy indication of the approach of a dangerous storm to the coast of British Isles precedes the storm by only a few hours. Delays are therefore very serious. It is admitted by the best British meteorologists that the observations of the United States are better conducted, although the best instruments in the world are set and registered at Kew in England. The work of weather forecast and storm warnings is carried on with a high degree of promptitude and efficiency at the Washington Central Office. This is because the work of predictions has been hitherto the chief work of the office. The entire time of observers, on whose telegraphic reports the forecasts are based, is controlled by United States Weather Bureau, and the right of precedence in the use of wires is maintained. Professor Bruckner, of Bern, has devoted a lifetime to the comparatively new treatment of climatic oscillations, based upon observations made at 321 points to the Earth's surface, distributed as follows: Europe 198, Asia 39, North America 15, Central and South America 16, Australia 12, Africa 6. One of his conclusions is that an average time of about 35 years is found to intervene between one period of excess or deficiency of warmth and the next, accompanied by opposite relative condition of moisture. All are familiar with the hoisting of cone warning as indication of a coming storm. This work is exceedingly important, especially for those connected with sea by business or pleasure. On the known approach of a cyclone, of dangerous intensity. Special messages are sent from London Meteorological Office, warning the coast likely to be affected. When the cone is hoisted with its apex downwards, it means that strong south or southwest winds are to be looked for. When the cone is hoisted with its apex upwards, it indicates that strong winds from the north or northeast are expected. Of course, they are merely useful precautions, but they are universally attended to by people on the sea-coast. Though one may have reasonable doubts about the use that can be made of weather forecasts for 3 days, such as now regularly issued, on account of the finical coy, spasmodic interludes on short notice, yet there are wonderful certainty in daily prognostics of the direction and strength of the wind, the temperature of the air, and the likelihood of rainy or fair weather, dependent on the broad uniformity of nature. This is very serviceable for people who have now to live at high pressure in business, in enthralling days of keen competition, and it is great boon to those who are in search of help by travelling, who, in innocent pleasure, desire to live as much as possible in open air. Very little credit is given to the guards of isolated weather prophet, but those who are confident in the usual weather forecast of the Meteorological Office are satisfied in their belief, and those who, in such confidence, ignore all weather prognostics are still weak enough to read them and act up to them. In practical meteorology, in the scientific explanation of popular weather law, and the study of atmospheric phenomena, which has so powerfully influenced us, for gladness or discomfort, we may, as with other branches of science, even all our days cheerfully go on in the noiseless tenor of our way, nourishing a youth sublime with the fairy tales of science and long results of time. End of chapter 35, and End of Meteorology, All Weather Explained, by J.G. McPherson. Recording by April Gonzalez in Cavite, Philippines.